All right, well then let's get started. I believe, Nicola, you are first.
By the way, before we start, I kind of want to apologize, but my voice is a little bit scratchy, so I'm gonna sound a little bit like an old man today because I have a little bit of a cold. It's not COVID, so that's a good news, but but still okay. So okay, great. So well, thank you everybody for having me presenting today. Although I don't work on blimps, a lot of research we do in my group actually relate a lot to some of the problems we discussed yesterday. So I'm going to go over actually some of the core things that we've been doing recently that actually fit very well with what could be work, for example, on blimps. So let me first, before doing that, let me give you a quick overview about what we do in my laboratory. I'm going to minimize this so I can see. So with my group, we work in robotics. So we are primarily again working on motion planning. And the whole goal of my team is to increase autonomy of autonomous systems to make them more resilient, agile, and safe as they move like through different type of environment, and they deal with different type of problems. Could be cyber attacks, or could be even like disturbances or failures. So in this slide you see some of the robots that using, and you're gonna see in the next slide. I'm gonna show some applications, some related to spot, some related to aerial vehicle. And we see how much I'm able to cover actually in half an hour. Okay, so these are some of the research that we've been doing in my team. So as you can see from this list, we work a lot with assured autonomy. We do work on runtime monitoring, predictive, proactive planning, control. We do some work on resilience against cybersecurity, cyber attacks. We're gonna see today some work on optimal planning, structured environment, some work also on offloading. We do some work on social planning, co-design, but for the most part, again, what I'm going to focus today is either these 4 items. I don't know if we're going to be able to cover everything, but these are the things that I think are more related to what could be, for example, some research on blimps. And specifically, we're going to be talking about, again, optimal planning and structured environment, and then some work related to how to deal with disturbances, so reachability analysis. Okay, so like everybody, most everybody, I also have a slide related to white blimps, and I think this matches quite well what has been discussed so far. So the pros, as have been pointed out yesterday, they are stable, they have low power consumptions, they can carry a large payload, that means also a large computer, we have long endurance. And what is interesting is also, like many other aerial vehicles, they can provide a large field of view, so they can assist, for example, ground vehicle or other vehicles. The con of this platform is that they're kind of related, they lack agility or maneuverability, so they're very bulky, so it's very hard to fit, inside indoor spaces. It depends on the size of the vehicle, and of course they're prone to external disturbances because they are so bulky. One other con that I didn't write down. It's a minor things, but people tend not to be very excited when you talk about blimps. So if you talk about quadrotors or like spot or ground vehicles, other type of ground vehicles tend to be more excited about the type of research. But again, that's a minor things. So here you see some picture about things and some research been going on blimps. I want to mention that there is a group at Georgia Tech that does work on autonomous blimps. I have a student actually working for that team. There's been some work on making hybrid blimps, excuse me. And Amazon has also been investigating the use of, well, it's not a real picture, this one, it's more like a prototype picture, but the idea of having like a blimp that can deploy the aerial vehicle so that it can go around and keep like this blimp as a mothership, so that it can go back, recharge, or take a package and go to the next town. Okay, so what I'm going to be focused on today is some of the research that I think are really fit very well with the pros of this type of vehicle. In particular, you're going to see some of the work related to how to assist other vehicles, for example, if you have a ground vehicle or another aerial vehicle in the field. Okay, so let me start with the first part. The first thing I would like to show you today is this work on navigating occluding environment. And the problem is very is very simple. And this regard pretty much any type of vehicle, not only blimps, but ground vehicle or any other aerial vehicle. The problem is the following. When a robot is moving like in a cluttered environment, there are a lot of uncertainties that you need to deal with. And these uncertainties are mostly due to occlusions. So as human beings, we are able to move quite well typically through like cluttered environment. If you are in an office space or if you're in a supermarket, you know how to, you know that you need to stop or something before getting to a corner if you know that it could be a busy time of the day. You peek around the corner, so you know how to slow down, you know how to take a different path. Robots nowadays don't do that, at least not yet. So what we target with this research is something very recent, is how we can consider what we call this known unknown area, that are these red regions that is here, that are regions that the robot should be able to see if you move in a certain way, but they're not visible, perhaps in the current position. So how we can consider this known unknown area and consider other factors about the environment to be able to create a more agile and safer motion of these vehicles. So you can think, for example, that if I'm in the middle of the night, this robot could cut through this corner. But if I'm during a busy time of the day, perhaps a better motion would be to promote visibility, so to kind of like move in a certain way so that you can gain more visibility around the corners. So what's the idea is that if you want to reduce uncertainties, this also will be linked to promoting visibility. So we would like to create a strategy that can do that autonomously, so that the vehicle is able to deal with any type of environment. So that's the problem. How we can combine safety, visibility, speed to make things more, to make a robot more agile, and to be able to kind of deal with this problem that you can encounter in clutter environment. So the first attempt to solve this problem, the way that we solve this problem was by to minimize this known unknown area, was to use MPC. And we've been talking a little bit about MPC yesterday, but the idea about these MPCs is that we have two competing objectives in this specific one that I'm assembling. We have one objective that is make a robot go faster. So by changing this waypoint, you can modulate the velocity in which a robot is moving through this environment. And then we have this extra term that we add to this cost function, but what it's trying to do is try to increase visibility around occlusions. And that in this specific case was dependent on the corners that you can encounter for like an indoor environment. So the first work that we did on this topic was, again, let's focus on indoor environment where we have corners, and let's try to see if we can leverage the corner to approximate this known unknown area. And we found this function that is able to approximate really well, actually, this area that is being found whenever the robot is moving around, so this known unknown area. Anyway, if you try to run this model predictive controller, that's the overall effect that you obtain. So if you don't do anything, if you put this weight here for this invisibility very low, you obtain that the robot just don't care, it just go around as any other robot does right now. By adding this visibility constraint, that you see that the vehicle actually does what we like. So it's able to scooch over, it's able to actually change its path. And while it's doing that, as you can see from this graph, it's actually lower this known unknown area. So with respect to the other simulation here, you see that the vehicle is able to improve the situation. Okay, to deal also with unknown, what we do, we also build an occupancy likelihood around the corners. So we also build a model that tells us, okay, how likely is that there is a person around the corner. And this model is probabilistic. That is we use occupancy grid mapping a technique. But at the end of the day, what we're trying to do here is trying to bring, this model that tells us, okay, if there is somebody or not, that could depend on the time of the day, or could depend also on some previous notions that you have from your environment. Anyway, based on this model, then what we want, we are able to come up, based on these probabilities, we can find what is expected distance to collisions, and then we know the model of our system, so how long it's going to take to stop, so we know the dynamics, and therefore we want to make sure that from any point, the system is able to stop, is able to react if there can be a person or somebody else that can pop up from that corner. And then based on that stopping distance, if it's violated, we can adjust the weight of our MPC so that we can move better with more agility around these occlusions. So let me show you an example. So in this example here, let me actually pause 1 second. In this part here where it's white, everything actually is safe. So we're assuming that there is no any problem. There are not no people around. It's known that everything is safe. But when we reach this corridor, we know there can be people that can actually cut through this corner. So what you're going to see is that in the beginning, the NPC actually make us cut through the corner because we're safe. But as we go through this corridor, we decide to take a different path so that you can take into account this uncertainty that are due to the fact that there can be people or other things that are moving that in that corridor. Let me show you the same case in case there is nobody. You can think of this as moving in the middle of the night. So there's nobody, we are sure there is nobody. So in that case, the robot is able to cut through the corner because we find that it's not necessary to take a longer path. Let me show you some experiment. These are some experiments in our lab. Again, deploying the same technique on a ground vehicle. And as you can see, these are two different paths that are taken if you consider the perception objective or not. On top, we didn't have a perception, on the bottom we had. And the overall difference you see it here that at the same stage, the robot is able to see more around the corner. As you can see from also this curve from this experiment that, again, we're able to minimize this known unknown area as a robot is moving if we have this perception objective. So, okay, great. This was our first attempt to deal with this known unknown, but this was limited in the sense that we are just dealing with the corner obstructions. While what we want to do is to be able to deal also with more complicated type of environment, like for example, forest or any type of environment. And on top of that, this extension that I'm going to show you now, we were able actually to deal with unknown environments, so things that are not known a priori. And even we didn't need to have like a trajectory that was computed a priori. So the robot just had a goal and was trying to minimize this known unknown as moving around. So we build on top of a previous approach. So we still use like MPC. We modify a little bit the cost functions, especially for visibility, and actually we create a quadratic function so that we are able to deal with this type of obstacle, with the circular obstacle. And then we use the circular obstacle around to be able to model any type of environment. So any type of environment that was built by superimposing circles. So if it was a forest, we're like circle around. If we're like a clutter environment, we just put it together a lot of circles. Anyway, we have, on top of that, we build some safety constraint that use reachability analysis to be able to figure out if we're going to be able to stop in time if we don't know what is around the corner. And we assemble everything together in like this big framework that you see in these pictures. So putting everything together that with this new approach, but also now we're considering really safety and adapting the speed of a vehicle, that are the things you can obtain, for example, in a forest. So in the one that you see on the top, we have this approach running with the safety but not perception. And you can see the robot here in simulation is slowed down as it's getting closer to this obstacle because it doesn't know what is around the corner. So it decides to kind of like slow down to be able to deal with these problems. On the bottom, you see actually when we add also perceptions, in that case, as it was in the previous case, we have that the robot actually changes path so that it can see better around these occlusions and at the same time also can move also faster for like this forest. So if you compare these two, these two simulations, you see that the blue one is actually with perception, and you see that overall actually we get a little bit faster speed around the environment. And at the same time, we're also able to minimize this known unknown area. So we're able to see better around this corner, around these occlusions, but is again safer because we don't know what is around these occlusions. Okay, let me move forward. I want to show some more simulations. This is another case. Again, here in the first one, I'm showing what happens if you don't do anything, because we're gonna get into a crash. Here, what happens if we don't consider perceptions, we end up slowing down, again, using the same approach now in an environment that is more like an office space. And this again is the same case as before, in which we have now with perception. And again, we see that we are able to improve visibility, the known unknown area get reduced, and the speed for this last one also get improved. We can go a little bit faster around the corners. As it was for the previous case, I want to show some experiment. So here you see a case in which we don't have perception, but just safety. So you have a spot with like a multi-leg robot, just moving autonomously around this environment, and it decided to slow down when it's approaching this corner because it doesn't know what is around this corner. If we add also perception, you see that spot is able to figure out that you need to actually take a longer path so that you can see better around this corner. And by doing that, again, is also able to maintain safer and more agile motions for like this clutter environment. So this, again, is an example how we can deal with occlusions, and this can be applied to any type of vehicles. But the way now we're moving forward on this research actually is to include more vehicles. So instead of only one vehicle, what we're thinking is something like this. And it's just this again is a prototype. It's not finalized, but the idea is, can we have perhaps, for example, here a quadrotor that can move, let's say, forward, okay, and kind of like and can kind of like provide some information to the ground vehicle that is in the back. So in this case, we are not doing that. It's just following, because again, we're prototyping this behavior. But the overall idea would be, can we have an aerial vehicle that can move a little bit faster in front of the vehicle and provide some information about, for example, is there anybody around this corner? Or is there any object? So that then we can pass some weight to the ground vehicle. In that way, is able to be prepared and be proactive as it's taking these corners and moving around. So you could think, for example, that instead of having a quadrotor, you could have a blimp actually flying way above and is able to inspect and get actually larger area, so that it can inform the ground vehicle about, for example, possible other vehicle or other things that are around these occlusions. But building on top of this idea, okay, about having multiple vehicles, we've actually been doing something that is really actually applicable to blimps. It's similar to what I've been talking in the previous slide, but the idea is the following: can we have actually a ground vehicle or like a base station or a blimp or something? Imagine this is a blimp that can assist an aerial vehicle or any other vehicle with limited capabilities as it's moving, for example, through like a clutter environment. So the idea is the following. We have, for example, this aerial vehicle, this drone, that is trying to move through a clutter environment. And it can use only local field of view. So it's limited from what it can do. And because of that, typically tend to move slowly if you're trying to move this vehicle for like a clutter environment. So the idea we would like to enforce here is that, can we actually use a base station? And let's assume that this base station has actually knowledge about this environment. He knows, he has a larger field of view, he can see better, know what is around. And can we actually offload some of the computations from aerial vehicle to the base stations so that it can actually promote fast motion for the aerial vehicle? So the aerial vehicle here, we would like to send a query to this, let's call it blimp. In this case, like it's a track, because we didn't think about the blimp for this research. But can we send a query, and then can the base station reply with a set, for example, a waypoint that the aerial vehicle can follow so that it can go faster for like this forest? So that's the idea. But as you can imagine, one of the problems with this technique is that we need to deal with communication delays, there are losses. So we need somehow to figure out a way also to deal with the fact that there can be issues with the communications. So that's sort of a problem. So we would like to make this, for example, smaller aerial vehicle move faster for clutter environment, while offloading computation from to a base station that can provide more information. Okay, so how do we solve these problems? So this is overall the idea. So we would like still to use MPC-like approach, and that's the reason we call this research, this technique, receding horizon. But instead to provide input to the systems, to the quadrotor, that will require like to have like very high frequency data that you broadcast. Instead, we broadcast actually waypoint to this aerial vehicle. So instead to have like a receding horizon controller that you're running on this scheme, we run what we call a receding horizon planning. So the base station, what it's trying to do here is not sending actually very frequent information about the input of a drone, but they're actually sending waypoint. And then we're leaving the low-level controller on the drone to be able to actually go to this waypoint. And that's the reason you see that this waypoint actually plays in a strange position, because actually these are going to be time waypoint. So by providing this time waypoint that are less frequent, what is happening is that the low-level controller is trying to go to this first waypoint, then it switches to a second waypoint, then to a third, to a fourth, and so on. But by doing that, we recreate a similar approach, similar behavior as if we are actually, the station was sending very frequent input as an MPC to the quadrotor. So by doing that, what you're able to do is that you're able to reduce the package, the communication package that you're sending. And by reducing again the frequency, also we are able to deal a little bit more with the problem that you can have with the delays. Still, there can be delays, there can be problems. So with the framework that I'm going to show you, that we create, actually, we can also adapt. We can actually learn about the delays that we have between a base station and a quadrator. And also we develop criteria to figure out when, for example, we need to switch back, for example, to a local controller. So the beauty about this approach is that whatever is running with this receding horizon planning is not running only on the base station, but it's also running on the aerial vehicle. The difference is that the base station has a larger field of view. So when we can use it, the aerial vehicle can go faster. If we had to switch back to a local planner, because, for example, the communication gets completely cut, then the vehicle ends up moving it to be slower, but it's still safer until it's able to regain communication with the base station. Okay, so long story short, the way that we solve this problem is, again, leveraging similar approaches as a model predictive controller, but instead of computing input to the quadrator, we compute reference waypoint that the system needs to follow. So we run this minimization in which the cost function, again, is similar to what you expect from an MPC, but the goal here is to find actually waypoint subject to a model of a systems, and knowing that there is a low-level controller that is acting on this quadrator, that could be PIDs, that make a system go through this waypoint. So again, that's the reason you see that this time waypoint has been created by the base station, they sometimes fall inside this obstacle because of their time. So what happens is that the quadrator starts to follow one, then you switch to a second one, then you switch to a third one, and so on. And this actually, what you see here is actually an example of one of the simulation we run on Python, running this technique here. So again, we are able to send waypoint where we don't need to send control input, and we're also able to deal with the latencies. So we build a strategy, and this is something we submit recently. And this strategy, what it does is pretty much, we send a query, as you can see here, to a base station, and then we expect to receive the response from a base station at a certain times. If we receive it at that time, that's great, we accept, and that's why it's green. But if we don't, okay, then we need to do something about that. So for example, if we receive it before, but everything is fine, because we just need to wait until apply our waypoint to a system. If a message is delayed, then we cannot accept that information. Let's say that the base station, now we get really far away and the communication get delayed, then in that case, we cannot use that information. So, but what we can do in that case is, for example, we can maybe continue using the waypoint that where we're sending the previous iterations, or if we see that the system is deviating from our desired path from the previous iteration that is computed, then we can switch to a local planner, and that's what is happening in this image here in the bottom part. So the system realized that it cannot rely on the previous waypoint, it cannot rely on the information from a base station, so let me go back to my local planner until I'm able to re-estimate the delay that I have between the base station. I can tune again back to use the base station. So again, let me show you an example. Typically, it's better to see for like some simulation. Here you see some simulation, which actually what is happening, the information are being accepted from a base station. We are learning the latencies. Differentiated of blue and white means there are different delays. White means actually it's a little bit faster. But you see that the system is able to, again, use information from the base stations and is able to be very agile as moving around. In the red region, actually, we lose completely communications. And you see that the system is actually need to switch back to its local planner. And that's the reason it ends up moving slower as it's moving through this forest, and then you regain information when you go out and you can move faster. The bottom one is another example. Again, white, blue region means there is different delays between base station and quadrators, and red means we lose communication. So as you can see here again, sometimes we don't accept, but we are able maybe to reuse again the waypoint were computed in the previous iteration. In the red one here, we lose completely communications. So the robot ends up switching to its local planner, moving a little bit slower until it's able to re-estimate the delay with the base station, and it can go back to move a little bit faster. So we run a ton of simulation on this. We are now in the process of implementing this on a quadrator. You can see here the difference between a local, if we do our approach versus if we just use our local planner with just with a quadrator, just with a quadrator without a base station. You can see that actually the time gets longer because the system end up again going slower for this environment. So this is an example where I can see actually the blimp could be used. So we could think to use a blimp as this base station that can foresee, can kind of like navigate, can understand where are the obstacles, and it can actually provide, because it can sustain actually a bigger load, it can actually carry maybe a bigger computer, and it can compute the solution, for example, for a quadrator, and provide the waypoint so that it can move around this clutter environment. Okay, so that's I think some of the research we're doing can be really deal with the blimps. I would like to take maybe like 5 minutes to discuss about another area that we've been doing in my group, but I think is also very relevant to research with blimp and in general research in robotics, to be honest. And it's the idea how we can actually deal with the disturbances or uncertainty again that really could happen at runtime on the systems. So a lot of research in my group has been centered already on this concept of can we build very fast runtime monitors that can really create proactive planning and control for example, for a quadrator, for any type of systems. So the idea is that you would like to be able to predict accurately, very precisely the future state of a system. You would like to make this prediction very fast. We would like to provide safety and liveness guarantees. We would like to minimize even unnecessary computation energy computations, especially if we know we are safe. Maybe we don't need to use a sensor very often. We would like to be proactive, be able to adapt the system if there are some problem, and therefore we need also to learn if there are problems in the systems, and then prevent unsafe situation if this happens. So at the core of this research, what we've been doing is really try to exploit reachability analysis. That there have been a lot of talks also yesterday about that. So ideas again about reachability analysis, is to be able to predict this region of future state where the system will be. So in order to that, the first attempt to solve this problem has been on, again, using like a pure reachability analysis, for example, Hamilton-Jacobi reachability analysis. In order to that, what we had to do is really, we had to use actually a correct model of a system. So we build actually equation of motion for our aerial vehicle. We consider disturbance models, power model our systems, even like how we build trajectories. And when we use all this information that are deterministics in a certain sense, to be able to create and predict what is the worst things that could happen. So one of the first approach for this runtime monitor was again to build this reachable set as fast as possible at runtime, integrating all this information about the dynamics, disturbances, failures, possible noise, disturbance that can happen. And then what would happen is that you can predict again where the system will be in the future. And we will obtain something like that. I will obtain like this cone that tell you, okay, this is the region in which a system will be, for example, over next couple of seconds. What is interesting is that if you're able to precisely get this prediction about the reachable set, then you can answer a lot of different questions. For example, if you know the environment, you can assess when it's the first time, for example, we can crash on an obstacle, or what is the earliest time which the robot can leave a sensor field of view. And then when you know that, then we can also think, for example, we could relax, for example, computations. If we know that I'm going to have, let's say, 10 seconds before I'm going to crash with an obstacle, perhaps I can stop using a sensor, or I can stop doing certain computation related to that sensor, and I can focus to do other type of tasks. And that was one of the first things we did, actually, that is here. So in this experiment, you see, and you can see the little quadrators that appear in RVs on the top left. These are the position where the systems figure out that you actually need to actually assess and compute and use the LiDAR, for example, information to predict this where it's going to go next. But you see, like in these long stretches, the robot knows that it's going to be safe, so it decides that it doesn't need to use actually it doesn't need to compute actually information from the LiDAR because it knows it's going to be safe. Worst case scenario is going to deviate a little bit from this path. So that again was one of our first attempt to solve these problems. What we did next, again, I'm going to have to spend a couple of minutes if I have.
Yeah, let me give you a 2 or 3 minute warning.
Okay, perfect. So now I might need 2 or 3 minutes warning right now.
Yeah.
Okay, so let me go really quick about that. So I'm not going to have time to cover this, but I want to tell you that what we've been doing is been like actually try to speed up this process. So one of the problems is that reachability analysis, you know, is very computationally expensive. So we're doing a lot of different, exploring different technique from using GP approach, as I'm showing in this slide. I'm gonna go over this really fast. But one approach that we've been doing really, that's been very, working very well has been actually bypassing completely the use of reachability at runtime. So one of the techniques we've been deploying is to use a neural network to actually approximate, to actually give us directly safe and unsafe decisions. So we train this neural network using reachability analysis offline to be able to tell us if something's going to be safe and unsafe. We also verify this neural network using this very SIG approach that has been developed by some of my colleagues at UPenn. And then at runtime, we just simply get the initial position of a robot, the final positions, and quickly we can assess if a system is going to be safe or unsafe without even having to compute the reachability analysis at runtime. So that's, again, an example how we can quickly do safe and unsafe decision-making without using the reachability analysis at runtime. And that's because we can leverage reachability analysis during training. So this is an example of a training. Again, I'm going to just go really fast over that. But just want to show you, again, we did the verification using hybrid systems reachability analysis. I'm happy to talk more about this, but just consider we verified that. I want to show you this before I conclude. This is an example again of our approach with the neural network based safe and unsafe planning. So you see here that the robot is doing just simply querying his initial position and final goal. And then he decides, for example, if it's going to be safe based on the strategy that he wants to follow. If he figure out that it's unsafe, he just change, for example, the avoidance distance that he want to keep from this obstacle, so that it's going to be safe, knowing that there are going to be disturbance, that can be disturbance in the environment. Anyway, long story short here, what I want to say is that we have also frameworks that are able to quickly tell us if something's going to be safe and unsafe. We use reachability analysis. And although I don't have time to talk about this, we also been exploring also technique to deal also with failures that can happen at runtime. And we have some very new novel works that allow us to learn at runtime. It's called meta learning, but allow to train special networks that give us that allow to just gain just a few data at runtime, and we're able actually to predict where the system will go in case of a failures. Again, I'm gonna stop here, but I'm happy to talk more about this technique. And we are, as you can see, we're very busy doing a lot of work related both to monitoring and planning for autonomous systems.
Okay, so good morning, everyone. So today I'm going to talk about data-driven verification and synthesis of autonomous systems, which can potentially be used for verifying and synthesizing controller for blimps as well, given that we heard yesterday their models is complex and sometimes is even unknown. Okay, let's see how can we attack this problem. I mean, I guess for this audience, I don't need to explain. Autonomous systems is on the rise. They're becoming ubiquitous. So because of the advances in computation and communication, but on the other hand, they also have very complex dynamics, right? And that makes it very difficult to come up with, model-based approaches, which have been studied in the past few years. So they are becoming more and more autonomous without human involvement. They are making their own decisions. And unfortunately, as most of us know, they are mostly built using heuristic approaches. So, I mean, not all heuristic approaches are bad, but for real life safety critical application, they can actually cause catastrophic events. And most of you heard about the Uber car crash, which happened, I think, 2019. So, and the reason I brought the Uber autonomous car crash because there was no corner case. The crash, in fact, would have been prevented using the basic safety mechanism that Volvo designed in their car. So that was like pure engineering mistake in their design of their autonomous systems, which would have been prevented easily if the system was designed in a better way. So, and also I was able to find also a blimps crash, right? To relate it to the talk today. So this is the Airlander 10 crash, which apparently the Airlander hit the power cable and that actually caused this crash. So in this case, there was no harm to the humans inside the airlander, but of course the price of the airlander, I think this was around $25 million worth of built of this blimp. So, okay, now what I'm gonna spend the rest of the talk is, we have complex systems, and for example, we have a blimp. The model is very complex, and as you can see, it's either represented using a differential inclusion or a difference inclusion, and now we are trying to actually design controllers for these physical systems such that some high-level objectives are fulfilled. For example, omega regular specifications, right? Or linear temporal logic properties. And what we want to do is, we would like to actually design the controllers in a systematic and machinery way, right? And preferably we try to have some formal guarantee. I mean, some sort of formal guarantee on the performance of the closed loop. So what is the challenge here is, we don't know the dynamic, right? Let's say the map F is unknown. And I'm asked, design a controller when the dynamic is unknown and you are given high-level objectives in the form of omega regular properties. So, okay, this is a challenging task. So let's see how can we handle this scenario. So before provide an initial solution to this problem, first, I want to introduce, I mean, most of you, yesterday we heard about barrier certificate, right? Let's see how the barrier certificate works. So if I have a system represented by this simple difference equation with the map F, here the set W represents uncertainty in the environment, or model uncertainty, right? And let's say I have two sets, x0 and x1. So if I can find a function b which satisfies these three conditions, namely if I know the function b for all x inside x0 is less than or equal to 0, for all x inside x1 is bigger than 0, and for all x and for all w, if the evaluation of b along the map f is less than or equal to b of x, then what I can guarantee is, if the trajectory of the system starts in the green region, x0, the trajectory never reached the red region, x1. That's what we get from barrier certificate. So barrier has been used a lot in the last 1 decade or 1.5 decades. And because of that, this paper by Prajna and Ali Jadbawai got HSCC Test of Time Award, right? Because the idea was very clean, doesn't require discretization of a space, and it can ensure formal guarantee on the safety. Of course, this idea can be extended to the synthesis as well, right? The previous slide was talking about verification. So what I need to do is, let's say my system also have another variable, epsilon, which plays the role of input, control input. And now what I need to do is, again, I need to search for a function b. The first two conditions are exactly the same as before. So you see in the last condition, I just bring an existential quantifier over the input. So if I'm able to find such a function, so that means there is a controller K for which can ensure trajectory of the system starting from green region never enters the red region, no matter what the disturbance is inside the set W, right? So, but as you can see in the previous slide and this slide, one of the key ingredients in order to find B using convex optimization tool is knowing the map F. But what if we don't know the map F? So what can we do? So this is how the main part of the talk will start. So what I plan to do is, I would like to collect data from the system, and in the high level, I'm also given high level objectives, Buki automata, omega regular specifications, and I'm asked to design a controller without knowing the model, namely the map F, by just looking at the data. So how can we do that? Using barrier idea. So what I will do is, I will actually cast this problem. Let's look into the verification for now. So what I will do, I will cast the search for the barrier function as a robust convex program, which is here. let's say I fix the structure of the barrier using this, linear combination of those basis function pj. So those pj are some user-defined basis function. Let's say in the case of polynomial type barrier, so pj of x, these are monomials, right? So what are unknowns? The qj, the coefficients of those basis functions. So I'm interested to actually search for those coefficients. So now look at this optimization problem. I minimize eta with respect to decision variables, which are the parameters of the barrier and eta itself, such that these three conditions hold. For any x inside initial region, barrier is less than or equal to eta. For any x inside unsafe region, barrier is bigger than minus eta. And the last condition says barrier along the dynamic is less than or equal to the barrier at the initial condition plus eta. And this last condition should hold for any x inside the state set and for any disturbance inside the set of disturbance. So let's denote the optimal value of this robust convex problem by eta star. So now you can readily verify that if I'm given a system sigma described by this dynamic, if eta star that comes from RCP is less than or equal to 0, that implies the barrier that comes from this RCP, namely the coefficients that comes from this RCP. So this function is actually a barrier certificate for sigma. So that ensures that if the trajectory of the system starts from x0, they never enters x1, right? But let's look at this RCP problem. This is very challenging. Why? First of all, if the dynamic is unknown, I don't know the map F. And second of all, this is a semi-infinite linear programming. Why? Because X is an uncertain parameter that lives in a compact set, in an infinite set, right? So this optimization problem is convex in terms of unknown, in terms of decision variables, but I am dealing with uncountably many constraints in this optimization, right? So, okay, so how can I handle that? So there are two problems.
Rashid, let me give you a 5-minute warning.
Yeah, so the map F was unknown and X and W lives in a continuous set. So, okay, what I will do is I will collect data from set X and W, finite data, right? N independent and identically distributed data sampled within X and W. And then I evaluate, I take measurement from the system after 1 unit of time, right? And I call those XI plus. So now I substitute those in the previous robust convex program, and now I call this scenario convex program, right? So now this is a linear programming problem, right? Which can be solved efficiently. So now the question is, what do you get if you solve this SCP? And let's say your eta star n, you get some eta star n. What can you claim about the original system? This is what we get. So if the number of data you collect from those set X and W, the number of data comes from this equation for some epsilon and beta chosen from 0 to 1, then with a confidence of 1 minus beta, this statement holds. If the optimal value of the scenario convex program from the previous slide plus epsilon, which will be used here to collect the number of data, is less than or equal to 0, then I can guarantee that the trajectory of the system with unknown dynamic starting from the initial set never reach unsafe region X1. In fact, I can also guarantee that the coefficient Q that comes from a CP is also give me a barrier function for the system with unknown dynamic. So what are the future directions or open problems? So what about synthesis of controller? What I showed in the previous slide was for verification. So what can we do for the controller synthesis? What if we go beyond safety, let's say omega regular objectives? And as you can see here, the number of data unfortunately grows exponentially with the dimension of the system. So now the idea is, can we propose modular data-driven schemes that can alleviate this complexity issue? And what about non-convex setting? This formulation holds if your optimization problem is convex. What if it's not convex? So what are the formulation in that case? So these are all future directions and open problems. And thank you all for listening to the talk, and let me know if you have any question.
I have one question, if we have time. Majid, when you said modularity in your last slide, what do you mean by that in this context?
So what I plan to do is, let's say I'm given a system in the form of interconnection of subsystem, right?
Mm-hmm.
So I can collect data from the overall system, or I can go and collect data from the components of the system. And what I will plan, what I can do is I can actually design local barriers. I don't call it even barrier because they are not barrier, right? Local functions based on those current data from the components of the system. And then what I can do is I can actually impose a compositionality condition under which I can compose those functions, and I can claim the composition of those functions is in fact a barrier function for the monolithic system. So that I can do. I mean,
interesting.
I hope I can do right.
Yeah, that would be, I haven't come across a lot of compositional research there, so that would be really interesting.
All right. Okay. So yeah, I'm Stanley Bach from the Department of Computer Science at Stony Brook University. About my research. So I have two parts to the talk. So I'm going to talk a little bit about my research, something interesting that I'm doing recently, and then talk about blimps and some ideas from somebody who knows very little about blimps on where they can be used. So traditionally, I work in hybrid systems verification using reachability analysis. So I've done some focus on systems where you have linear differential equations or piecewise linear differential equations, you have inputs, and how to do reachability analysis, how to do that efficiently, looking at very high dimensional reachability analysis. That was a recent result from a couple of years ago. And so reachability analysis is trying to compute, it was used in a couple of different talks. So it's roughly, you could think about it as trying to compute the sort of set of states of the possible states that a system can enter under some uncertainty. So it could be uncertainty in the initial states, uncertainty in the external inputs or disturbances, or maybe there's some uncertainty in the model as well. And so a lot of it involves geometric reasoning. When you're doing it for linear systems, you care about operations like affine transformations of sets of states, and being able to do this efficiently then in high dimensions. So beyond that, that's useful when you have systems with differential equations. It turns out the same types of operations you need to support efficient reachability analysis for linear systems, when you have linear differential equations, are very useful for proving properties over neural networks. Neural networks, the sort of basic setup, you have weights matrices and bias vectors at each layer, right? And so that's, if you have fully connected layers, there's convolutional layers. You could also write like that, although you don't usually explicitly write the weights matrix, but it's still a linear transformation. And many other layer types are also sort of fall into the same property. And there, the challenge is the hidden layers can have a large number of sort of hidden units, and that determines the dimensionality of the spacer. And if I took a set of states and I wanted to propagate it through a neural network to prove properties over sets of inputs, I would need to be able to perform essentially linear transformations plus bias vectors, so affine transformations in high dimensions, which is exactly the operations we needed before. So I've developed tools then to be able to apply geometric methods, reachability methods, to be able to prove properties over neural networks. Over this last summer, there's a competition on neural network verification that we've helped organize. So I think the VNN comp, it started last year and was sort of a friendly competition where people submitted their own results. This summer, we actually ran things on common hardware, and we had, I think, like 10 or 12 different tool authors from around the world actually tune their own tools on common benchmarks. So I think it's the best comparison so far of the state of the art for neural network verification. And so that's an area I'm very much actively interested in as well. The things I want to talk about today focus more on these sort of bottom two pictures, and this is dealing with testing-based methods, right? So the top one's reachability. You're doing set-based analysis. The bottom one was looking at this autonomous racing overtake problem. but in the context of test generation, right? And so some motivation for this would be something like the Autonomous IndyCar Challenge. So this is a real thing. So people went to Indianapolis, the Indy 500, and they raced full-size cars actually last weekend. So it's something that just happened, but it's been sort of in progress for about the last 2 years, where there was, initially over 30 universities that were interested, over $1 million prize pool, right? So people sort of took this, I would think, pretty seriously, right? This wasn't just a grad student working on a toy problem. And so before I talk about the results of the actual race, I'm going to talk about the results of the simulated race. So there was a simulated race in June for this particular, the Indy Autonomous Car Challenge. There's this sort of high fidelity simulator that was provided, and 16 teams participated. And you can see here are the qualifying times for the single car races. And every car did really well. I think the top 14 out of 16 cars were within 1 second of each other in terms of the single lap time. The teams did pretty well. Everyone was pretty close, and the cars ran fast. However, when they started to do head-to-head races, some problems start to come up. So this is just sort of some clips from the race that occurred, where they had multiple cars run against each other. They had different heats, and they ended up having to restart the race a number of times and continuously keep disqualifying cars for either crashing into each other, crashing into the wall, and things like that. So while in the single car case, it was sort of, it seemed like all the teams succeeded in developing sort of efficient autonomy algorithms, when they were in this multi-car scenario where you're trying to balance high performance with safety, and there's maybe some aspects of the system that are unknowns, like the behaviors of the other cars. The situation was a lot harder, and it wasn't just sort of one team or two teams that failed on this. This was multiple teams that failed. And so 12 out of 16 cars were disqualified in the simulated race, and the first place car actually just had first place from the time trial and never had to actually do an overtake maneuver. So this is showing the challenge of developing overtake maneuvers. And so one of the reasons that we predict this happened is that testing for things like overtakes is sort of difficult. So running the simulation takes a long time. The simulator that was provided to them, it's much slower than real time. It's very high fidelity. And if you do sort of a full simulation where you do maybe 10 laps, there might be only 1 or 2 cases where there was a situation where there might have been an overtake, right? So it's not really efficient testing. So this was the research area that we were trying to address. And so what happened with the real race? Well, they decided after lots of testing that they weren't going to do any head-to-head races. But even without this, there were still 4 vehicles that managed to crash into each other. And so this is sort of one example of that happening. I think a lot of it was there were sensing issues, which can come up in autonomous blimps as well, right? And so there's this Twitch channel. You can see all the clips of this race too, of the cars crashing into each other individually. So it's still a challenging problem. I mean, there was still some progress with this. I think they did set the world record for fastest autonomous car, right? It was 60 or 70 miles an hour. So cars did drive fast eventually, but again, no head-to-head races. And so one of the research things we were developing was, how do you test these types of systems that are sort of difficult to test if you're just doing sort of scenario-based testing? And so there's this deterministic simulator for the F110 competition that we evaluated, that we tried to use for testing. And what we did is we looked at different disturbances that can come into a system. So this is a deterministic version of the F110 simulator. So if you run the same scenario twice, in principle, you'll get the same result. So maybe you'll see a crash, maybe you won't. But by doing sort of slight disturbances to what the sort of nominal behavior of the system, you can create very realistic cases where there's crashes that you find. And so what are these disturbances? These were, we would slightly alter the gains of the opponent vehicle in a head-to-head race. So 2 vehicles would race head-to-head, and then by slowing down the opponent or speeding them up slightly, you're able to create vastly different scenarios. And then some of those lead to crashes, some don't. And then the question becomes, how do you search this efficiently? So what's shown here is 2 different search strategies. So the one on the left is randomly creating these disturbances. You can see this does find a number of crashes. So these circles, as well as these red X's, are crashes that are found after some certain amount of simulation effort that was put in, but they're fairly clustered. And so the reason for that is a lot of times you'll crash, for example, on the first turn. And then, so while, if all you're doing is counting the number of crashes, this is a very efficient testing mechanism. But if your goal is to generate a variety of crashes, that, something that can help a designer debug a system, ideally you wouldn't want, basically the same test case a large number of times. So we propose this sort of sampling-based search, which uses sort of like a modification of RRT inside what we call an objective space. And so it uses something like RRT so that as soon as you have a case that gets past the first turn, that's the one that will be continued instead of always starting from the start. And that allows much more exploration. So if you look at the crashes here around the track, you can see that almost everywhere on the track you could find a case where there'd be a crash either due to overtake or a vehicle crashing into a wall. So these are both drawn with the same simulation effort. But the one on the right, I guess, has sort of intuitively better coverage, right? There's more of these clustered collisions at different, especially near the end of the track. You can definitely see that. And what do these crashes look like? So here's a video of the deterministic simulator, and you can see some examples as you sort of go to further and further down around the track. You can see that the different types of crashes are found. And so the ego vehicle here is the one in the back. It's the one shown in pink, and the sort of brown one, I guess, is the opponent vehicle in this case. Let's let this play out. You can see how there's collisions different track. And of course, this depends on the specific controller too. So another thing we evaluated was 5 or 6 different control strategies. And they all worked to different degrees, right? So some of them are worse than others. But generally, this matches sort of the pattern found during the F1 10th competitions, right? So they've still been doing F1 10th competitions recently. They've been virtual, and for the people who can't attend places in person. And so the most recent one, I think, was also a couple weeks ago, and I think what some of the results are that when cars are going close to the same speed, there's hardly any overtakes, right? So it's very important to be upfront at the beginning. And so this sort of matches that, right? So when cars are at the same speed, you can find a lot of collisions and overtakes. So this helps hopefully to develop better logic. Okay, so enough about testing safety, high performance, safety critical CPS. Here's some ideas I had for different blimp applications, right? So this is my picture of a blimp. And so, I mean, a couple of times people have mentioned these hybrid blimps, right? And so this is related to my first idea. So you could have this sort of two-way pump where you can inflate and deflate the balloon as well. And hopefully what this would allow you to do is sort of convert between lighter than air vehicle and heavier than air vehicle. So I think this is interesting from like a hybrid systems perspective as well, right? Because you're switching between these two modes that are hopefully better understood. So if you deflate, then you can have more maneuverability. For persistent autonomy, this might be good too, right? So for the military application, you have the blimp with the camera looking onto some city, and then when you want to move around, you can switch to a more maneuverable version. Or if it becomes unsafe, then you can fly away, right? And so this could also be like something more like an aircraft instead of a helicopter. This was the first idea I had. So that's idea one. Idea two, so you have this blimp, and so you'll have multiple of these blimps. And so I guess I didn't know there were only 25 blimps in existence. So maybe this is a small balloon that has a propeller on it, let's say, something that we could build. That doesn't cost $25 million. And so what could you do with this, right? So we had multiple, I think coordination of blimps is an interesting application. So here my idea was we could put lights on them, right? So we have these LED floodlights that we put on all of these. And then because they're blimps and they're slow moving, maybe you could coordinate them that you could somehow hook them up together, right? So you can hook these up to a power source so that you're actually getting power from the ground. And then you could do things like, put lights where you normally wouldn't have lights. Like if you're doing some search and rescue at night, assume that you can control well enough or there's no wind, right? Nothing interference. Could you, create lights over a forest, right? Or if you want another application, people, if you have an outdoor wedding, right? So your options now are you can buy a tent, but if you could, suspend balloons that aren't too noisy that float above, you could also have, a light in a field. That would be kind of nice. So that's the second idea. And the third idea relates to this. So this is Cyberpunk 2077, right? So this video game came out at the end of last year. I heard there's issues with the gameplay. I haven't played it myself, but the visuals are very beautiful, right? And so the idea relates to not the police blimps that you see sort of floating around here. I think those are police blimps, but actually these lights, these hologram things, these are really cool. And so I was wondering, why don't we have these in reality, right? So we don't have holograms, but can we pretend we do? Can we do something similar, right? So here's the idea, right? You have a bunch of blimps, again, that are coordinating with each other, and you suspend little screens off of them, or LEDs hanging with ropes. This could be meshes as well. I don't know what makes sense. And if you do this at night, you won't even see the blimps, right? And they won't be loud. All you'll see is the lights, and then you somehow have a good synchronization between them, and then you can display advertisements, right? And that's worth a lot of money. And so, I mean, people have light shows with quadcopters too, right? And so there is a place for this. You could imagine you go to a sporting event and you see one of these large beams that goes up 1 kilometer. Maybe it doesn't have to be that high, but it goes up into the sky. It could be some sort of novelty to have. And so those are the 3 ideas, and that's also the end of my talk too. So I don't know if you want to improve upon these, or there's any questions on the earlier material too. I'm happy to answer that. Thank you.
I see Cody has a raised hand.
Yeah, could you go back to the, oh yeah, you have it here. This is good. So what's the concept between converting from a blimp to a helicopter? Is it that you would eject the balloon part, or that you like, I see the empty balloon, so it's just hanging there. Do you stow it, or?
Yeah, ideally you probably want to roll it up somewhere or something. The idea is you compress the air, right? So you'd have some sort of storage tank for the air. So if you compress the air, this will become heavier.
Interesting.
And then you can fly, right? And then you're heavier than air vehicle. Yeah, you probably don't want this hanging off, but
yeah, and then you could go back to blimp mode.
Exactly. Yeah. So when you're loitering over a city or target or something, you use the low power blimp mode. But then if you need to move around more, you could use the more agile helicopter / fixed wing vehicle mode.
Okay, cool. Yeah, that's a very DARPA-y idea. I think that would be, I mean that as a compliment too.
Okay, good.
Okay, sounds good. Thank you for having me. I was just going to give a quick talk on some of the work that I've done in the past related to prediction and planning, and how that might be applied to lighter than air vehicles such as blimps. I think we've kind of covered this, and it was covered pretty well in the website for this. But there's a lot of potential benefits of using blimps, both for its ability to focus on endurance. It's a good platform for persistent autonomy. They're slow, non-agile platforms, but they can also handle computational delays. But I kind of want to focus, I guess, similarly to what the other presenters talked about, what are the main challenges, right? So need to be able to kind of handle these large environmental disturbances. I think the website mentioned, they're challenging to control, but I think a corollary to that, given its nonlinear and time delayed dynamics, a corollary to that is, it's also hard to estimate its own internal state. And I'll talk more about that. And then, it requires innovative control and planning strategies. So, I think there's some work that I have done with some other members at Johns Hopkins, kind of focus on long horizon prediction and how that can be leveraged to improve safe operations. Also looking at things like taking traditional common filters and incorporating a deep neural network to estimate some of the harder to model dynamics, as well as some of the state transition blocks of the common filter for state estimation. And then, if I have time, kind of just briefly touch on some of the work that we've done with sampling-based control strategies that allow us to, not require explicit dynamics models, but more of a sampling strategy for dynamics. So, I think kind of this dovetails pretty nicely with Nicolo's talk. He's kind of looking at, how do I develop a controller that can increase the ability to see or build an occupancy map around where you have most uncertainty or least amount of information. I think this talk and this work is similar to that, but it kind of focuses more on the perception problem. And in that, effectively you're fundamentally limited by the line of sight of a sensor. So if I have a LiDAR, it has some range, and if I'm about to turn a corner, it really won't be able to see around that corner. And so what this work is leveraging is can we learn predictors about the environment that act as predictors of occupied spaces beyond the line of sight of the sensor. So the intuition here is, you're walking around a corridor, you don't stop, rescan, replan, and execute. You kind of have this predictive model of what you expect to see around that corner because you've seen corridors before a million times. And so the idea is, can you learn these spatial features of these indoor environments, develop basically a predicted version of the occupancy map, and then use that as part of your planning algorithm. And so, the work we're doing is really, leveraging kind of off-the-shelf planners, but kind of doing ablation studies. If I just looked at the horizon from the sensor and then looked at this predicted region, how can that improve my performance? And so the first thing we kind of looked at was, this information theoretic exploration. So, if I make a prediction of the environment, can I use that prediction to efficiently explore the space better? So if I just kind of drop a robot in the middle of a room and I want to build a map of the environment, can I basically make predictions of the environment? Can I make multiple hypotheses of these predictions? So, if you have uncertainty associated with it, your multiple hypotheses will have variance. And that's kind of what I'm showing here is when you make these multiple hypotheses, you can look at basically the variance across these and use that as a heuristic to, explore the space. So it's kind of like, if I make multiple guesses and they all diverge in this one region, that's probably the area that I want to go explore. And so we kind of exploited this property and used that to improve exploration strategies. But then I think more importantly, really indicating, this unknown region, right? Can we leverage these generative neural networks to predict occupied spaces beyond the sensor horizon, and then use that for higher speed navigation? And so this is basically using an MIT race car. We're using basically an RRT planner, but again, kind of looking at the comparison between just from the sensor horizon and then leveraging the predicted map and seeing if we can travel at faster speeds. So here's just a couple of videos. Basically this is just showing 2 meters per second without using the prediction, and it gets there, but it's kind of waves back and forth because computationally it's trying to build this map while it's trying to plan, and so it updates and then it recomputes a new knot point. It doesn't actually hit the wall, but obviously isn't very smooth. When we increase the maximum speed to 3 meters per second, you can see basically it now tries to move too fast, and it's actually not able to compensate for that slow map update. And then here's now, I guess, with the prediction, and you can actually see the predicted region in the occupied space. It's like the grayish area. And here now, because it's actually able to use that predicted occupancy map, it can plan at a longer horizon and be able to kind of navigate that turn a lot smoother. So, I guess just to kind of focus on, applications to lightweight aerial vehicles, we've done work with just occupancy maps, static obstacles, based on the geometry of the room. But we've also extended this to dynamic obstacles like pedestrians and how robots can use the prediction of pedestrians for navigation. But I think what could be interesting too is really thinking about this in an application of persistent surveillance, kind of, being able to predict future positions of targets and then kind of learning where to look next, right? Because you don't have the agility of a lightweight with the lightweight aerial vehicle, you need to do a better job of knowing where the target points are and having that longer horizon planning. So that's one area where I think this could be leveraged. And then also, being robust to environmental disturbances, right? Everything I showed was kind of static obstacles in the environment, but if you can kind of predict what kind of environmental disturbances are going to occur, different weather patterns, different obstructions, occlusions, if you can model that and predict that, that could also improve the safety of these systems. So the next thing I'll talk about is using these common deep recursive filters for out of distribution state estimation. Again, we talked about, with these lightweight air vehicles, it is really hard to control and estimate the state because of the nonlinear time delay dynamics. And you think about when you're doing state estimation for an aerial vehicle, you have to have some kind of mapping algorithm or SLAM estimation for knowing where the blimp is in the environment. And so, the idea is if you're starting to get occlusions and a lot of noisy observations, how do you make sure that you're robust to that? So some of the work that we've done and published in ICRA last year is this notion of, how do you combine, elements of a neural network with a deep common filter framework, where you actually try to, the idea is, typically you have a perception pipeline that estimates some state variable, and then that state variable becomes the state of the system, and then you propagate that through the common filter. But you lose a lot of information when you try to decouple those things. And the idea is if I coupled it, where I can now operate my common filter framework on an embedding from a neural network, can I get access to some of those lower level features that may be more robust to noise? And so that's the idea here is, can I leverage kind of this common filter framework to measure the uncertainty of state, as well as a learned dynamics model. So I don't have to have an explicit dynamics model, but I'm learning those characteristics at the embedding space itself. And can that give me more robustness towards state estimation? And so really looked at in this work kind of to a simple problem of like a noisy pendulum, which, the pendulum is the easiest dynamical system to follow. But here, you're kind of trying to estimate the pendulum angle given, a sequence of images. And the idea is that when you get to like a lot of noise in these images, can you still be robust to estimating that state, given, that you can barely see it? And then extending those simple idea, this idea from the simple experiment to something more complicated, like detecting pedestrians, in the presence of noise. So, as I add more noise to the observation space, can I be more robust to that by leveraging this deep recursive framework?
Let me give you a 5-minute warning.
Okay, sounds good. And so here we're looking at, basically just, the properties of a common filter, right? Being able to leverage this, the mathematical framework, but operating on the embedding space of the image itself. And one thing you want to note here is, in terms of the uncertainty, you want to be able to capture that in the covariance matrices of the common filter. So if you're not sure about your state estimation, you want that uncertainty to be high. But as you train and get better at the data, you want the uncertainty to be low. And so here we're basically just looking at, basically two properties, leveraging this deep common filter framework. So as we increase the noise of the observation space, and now specifically it's out of distribution, can we be more robust to the state estimation, looking at, comparing it to, just having no dynamics model, just a simple LSTM, versus, taking kind of the state of the art state estimation for pedestrians and comparing it to ours. And what you want to see is, is the actual mean average error of the pedestrians lower? And then also, how are you doing in terms of uncertainty? And so we're showing pretty significant improvement in terms of that. And so again, kind of just applying this to lightweight aerial vehicles, we think about kind of traditional state estimation for a blimp would be an overhead camera image, maybe integrated with an IMU with some GPS. If you take away the GPS and now you're kind of only relying on the inertial and invisible features for state estimation, you kind of fall into this trap of, estimating the state even when you're occluded or if the images become noisy. Can you be more robust to that? So I think, applying some of these common filter techniques, but on the image embeddings, can give you a more robust state estimation in GPS denied areas. And again, I think a corollary to that is you'll be more robust to image noise and occlusions. And then just really quickly, I'll just end with this, in terms of controls, we've been doing a lot of work with complex terrain prediction and navigation. So can we, predict, use a sampling-based strategy to navigate around different environments? And so here we're basically just trying to estimate where in the environment is, can I navigate through? So, if it's tall grass, I can go through it. If it's a big bush, I'm not able to go through it. And can I use the network to be able to learn that? And then can I sample the trajectories to find the trajectory that's most optimal for that, to basically go towards positions where I can actually traverse and where I cannot traverse. And so again, I think not having a full pipeline of control of, having a perfect dynamics model, some of these sampling based strategies can help with the vehicle, with the lightweight vehicles as well. So with that, I'll end and answer any questions that you might have.
I had a question. So when you talked about the predicting the occupancy map and going through the corridor and predicting that, buildings are not so different, right? Do you really need the neural network kind of machinery? Because in the end, architecturally, buildings are very similar. If I were to look at, I guess I'm not predicting the global map, right? In that case, it's very different, but locally, buildings are pretty similar.
Yeah, I would say that if you're just looking at kind of office-like environments where you have maybe like right turns and long corridors, but if you think about like an atrium, right, that becomes much harder to model and be able to estimate a prediction model there. And so that's where I think trying to incorporate some of these techniques does help. And so I didn't show this video, but there is, it does work pretty well on like the 90-degree angles, but also like when you get into these wide open spaces and being able to predict these nonlinear, complex environments, I think it becomes more necessary in that.
I guess in that case, there might be an option of just feeding architectural plans beforehand instead of.
Yeah. I mean, if you have an architectural,
on
you should definitely use that. This is more for, a new environment that it's never been, and there's no pre-existing map. Exactly.
Yeah, and much like models of systems, I think architectural diagrams are, probably at most 80% correct. So you'd want to have some doubt when you were using your floor plan.
All right, so hi everyone. My name is Hanso Yoon. I'm a PhD student at the University of Colorado Boulder. As you can see on the schedule, Suram was supposed to give a talk today, but yesterday he asked me to present my work because he cannot make it today. And the Adita agreed, so thank you for giving me this opportunity to present my work. First of all, I want to mention two things. First of all, if my voice is unclear, please tell me. I got my booster shot on Monday and I was really sick and still sick. And voice is weird. And second, Suram did not told me that this is about the blimps, and I have no single page for the blimps, and I'm sorry for that. But I'm personally very interested in this idea. I think this is a great idea. I haven't thought about, because I'm a PhD student, but at the same time I'm the Air Force officer in Korea, the active military officer. So I think that this can be applicable in many areas, and I really want to see how the Galois make a progress on this, the police idea. So okay, so let's get started. So here I'm going to talk about predictable runtime monitoring using logic-based Bayesian intent inference. I think this idea still applicable to the police. So maybe don't need to explain a lot of the background, but as we all know, the unmanned robots are increasingly common in crowded urban spaces, and it becomes more important to track the robots over time in order to detect and prevent property violations, mostly safety violations, in highly dynamic environments. If we fail to track such robots, it may result in dangerous situations like we saw in the England maybe 2 or 3 years ago. Of course, this can be happen. And this is also important for blimps because the blimps should know the future trajectory of other flying robots, like drones or other blimps, to avoid collisions. So I think that's still important. But unfortunately, detecting such violations at design time is often impractical. Behaviors are dependent on possible environmental conditions. The space of possible behaviors is too large or may not be completely known to the designers. So we need a rigorous monitoring framework for unmanned robots. So the problem we wanted to solve is forecasting future trajectories of robots. So let's see this yellow robot. Like I mentioned in the previous slide, the space of possible behavior of this robot is too large. We can predict future positions without knowing what the robot can do or what the robot wants to do. So simple approach like extrapolation is not a good solution to this problem. Extrapolating the past trajectory is often likely to fail unless we know a specification of the task that a robot is performing, like this. If we consider all possible control inputs of the robot, we can get a something like the retrieval set, something like this. That is too conservative. And if the prediction time horizon is large, we get like a bigger retrieval set for this robot, and this is not a useful information. One idea to solve this problem is to consider the robot's intent to bias the future predictions. For example, in this case, the robot's actual intent is avoid the mountain, this is mountain, and then avoid the mountain and reach the right bottom corner. If we know that the robot wants to avoid mountain, we can get a better information about the future behavior of this robot. Maybe we can still make like a retrieval set, but we can make this smaller retrieval set following the intent. So we will use the robot's intent or high-level mission in this work. Also, we assume that the robot chooses an efficient path or efficient plan for implementing the mission. The efficient path can be either the shortest path, let's say the robot move from A to B, can be the shortest path or the almost shortest path. In many scenarios, this assumption is reasonable since people want robots to implement more missions with limited resources. We don't expect we don't want to make a robot go like this. We have one more assumption. We assume that the full knowledge of the map is available at any time. This is important because we cannot generate hypothetical intents without the map information. So in this example, we know there are 3 buildings, A, B, and C, and the mountain in the middle. So in this work, we use the robot's intent information for predictable runtime monitoring. Our assumption is that if a robot has a high-level mission, we are able to not only infer the mission by observing robot's behavior, but also use the information to predict future positions. So the ability to find the intent is the key in this work. This is the proposed framework. This framework consists of 2 phases, hypothesis generation and hypothesis evaluation. We first generate all possible intents based on map information, like this H1 through H3, and generate an efficient trajectory corresponding each intent. Then we evaluate intents based on robot's behavior. To do this, we use Bayesian inference. I'll show you more details in the following slides. So this is the detailed framework. Let's see this step by step. I'll start from this hypothesis generation. First of all, central to our framework is a map of the robot's workspace that is discretized into finitely many cells. So we use the mathematical model of a transition system. Here, there is a finite set of cells here, and the arrows represent the possible moves from one cell to the next cell by a robot. And MBG represent atomic propositions, mountain and building and goal. To express robots' intent that is unknown to us, we use the linear temporal logic formula involving atomic proposition in the map. For example, avoid region P can be represented by always not P. Everyone knows about this. And reach P while avoiding Q is expressed by eventually P and always not Q. Once we have all intents written in linear temporal logic, we translate all into Buhi automata. We use the tool called Spot to do this. Now, using linear temporal logic, we can rewrite all intents. So here, the go to A can be the eventually A, something like this. Finally, we will compute the shortest path from the current position to the goal position using Cartesian product of transition system and Buhi automata. Let's say we have a simple map, as you can see here, and one intent, reach goal while avoiding mountain. And this is the product automaton of the transition system and the Buhi automaton we saw. The product automaton models all the joint moves that can be made by a copy of the Buhi automaton in conjunction with the transition system. Finally, we can simply find the shortest path from the, let's say this is the current cell to the goal using simply any shortest path algorithm, like a Dijkstra algorithm. For all intents in a hypothesis set, we compute the shortest path cost and then pass this information to the hypothesis evaluation blocks. So in this example, we have like let's say that we have the 4 intents here. Looking at the map, we can generate this intent. And then using the Cartesian product automaton and then the shortest path algorithm, we can get the cost.
Let me give you a 5-minute warning.
Oh yeah, okay. So let's see the hypothesis evaluation. The core idea of a hypothesis evaluation is like this. If the yellow robot moves from here to here, we may think that the robot's intent is not the visit A, because the robot is not following the shortest path of visit A, this one. The robot's move is not efficient in terms of that intent. To compute the probability of each intent, we first need to compute the probability of moving from current cell to next cell when following an intent, let's say phi. To do this, we used something called the Boltzmann noisy rationality model. In this model, the probability of moving from the current cell to next cell is proportional and exponential of the sum of the cost of moving from the current cell to next cell and the cost of achieving goal from next cell. That is, this model returns high probability if a robot is following the shortest path of an intent. Let's see this example. The robot is moving to the goal position represented by a flag here. But we don't know whether the robot will cross a river or avoid a river. This is the river here in the middle. And robot's path position is a purple dot. And robot just moved diagonally. The probability of this behavior given hypothesis 1, cross a river, is computed by Boltzmann model. So in this case, we know the cost from the path position to the current position, let's say the 1.4. And we can compute the cost from current position to goal using a shortest path algorithm. We can compute this cost. And with an appropriate normalizing constant, we can get the probability of this. So in this case, this path is longer than the shortest path of the cross river. So we get the lower probability. Then we can finally compute the probability of each intent using Bayesian inference. So using the probability of a robot's behavior given intent and the prior, we can get the posterior of intents, and this will be the prior of next computation. So we compute this again and again. Once we get the probability distribution of intents, we can predict the future positions of a robot. So let's say that we have the 60% of probability for this intent, 40% for this intent. Then we can predict the future position of a robot by drawing posterior predictive samples using a Monte Carlo simulation like this. So, okay, now I have 2 more minutes. I'll show you some experimental results. First, I'll tell you the meaning of each figure. The green areas are regions of interest. A robot may visit a region or avoid a region, or visit one region while avoiding another. These red dots represent past trajectories. We assume that our framework already updated the probability of all intents during these past moves. So here we have some probability distribution. So robot head represents the current position. This light red line shows the ground truth future trajectory, which is unknown to our framework. And this is the future position we want to predict. In this example, the position of seven steps ahead. Gray and black rectangle shows predicted position generated by our framework. Darker shades represent high probability. So in this example, so a robot wants to avoid all these big regions. It can be like a geofence for the blimps or something like that, or wall. We don't know what this is. And these regions are, no, so sorry, this is not a wall. So the robot can pass through them. That means if we don't know the intent, our prediction results may pass through the regions. Something like this can be possible. However, our framework learns the robot wants to avoid the region, so it predicts the positions accordingly. So even here, our framework does not predict like this, it knows like this. So the same thing again and again. So here's the prediction accuracy and the computation time. So our framework degraded as the prediction horizon grows, and when more regions or more intents are considered as expected. Nevertheless, our approach continues to provide useful information nearly 70% of time on prediction horizons that are 10 steps ahead. And the computational complexity of our approach depends on the size of the product automata and the number of hypotheses we tested on Python, and the computation time was a tiny fraction of the overall time horizon. So pretty much this is all. I think the time is over. And thank you for listening to my talk. And if you have any questions, you can leave on the chat or the docs. I'll monitor that. Thank you.
Hello, so this is our talk, Build Your Own Balloon, BYOB, and it is to talk about our planned efforts at Galois to build an indoor blimp that can fly around and demonstrate cool things. And so this is work that myself, Sam, and Michael have done. So when it comes to the Balloween theme, I think that this talk is interesting in the sense that we have a lot of things that talk about why we may want to look at lighter than air airships or blimps, but this is to go a little further and say why we may even want to design these things in the first place, that is, create our own vehicles and try to sculpt out our own open loop dynamics for these things. So when it comes to looking at blimps, they have a lot of known pros and cons, and ones that have been mentioned before. That is, they have superior endurance and range. When it comes to their weight, they don't weigh a lot compared to what they're able to carry, and so they have good efficiency in that way. And they also can provide a platform that has lower vibrations due to the more diverse ways they can generate propulsion for themselves. And on the con side, they are large in nature. They are essentially large bluff bodies, and as such, they can be easily disturbed by their environment. And they typically have maneuverability concerns. That is, they are not very agile vehicles. And so the reason why this design problem was brought about at Galois was there originally was interest in potentially having this lighter than air airship do something kind of exotic, which is to play team sports like Quidditch. And so we know that we potentially want to have a buoyant airship in that space because it needs to endure throughout an entire game without needing to recharge. But when it comes to things like that, maneuverability may be something that you would want to get back. And so when it comes to looking at what you can design in an airship, you may want to start hybridizing. That is, you may want to start going into certain areas of the design space that are not conventional when it comes to blimps. And so this poses a challenge to us, which is, can we design a hybrid airship? And can we do it kind of in the indoor enthusiast space where we're not necessarily going into high altitude or extreme environmental conditions, and do it fairly cheaply? So on the right, we see kind of the trade-offs that we have when it comes to looking at ways we can generate lift for an aircraft. And so there traditionally has been lots of vehicles that exist on the corners here. That is, they do so aerodynamic at cruise flight. That would be the top. And you would see things like gliders and fixed wing aircraft. There are propulsion aircraft, and they typically have great maneuverability properties and low endurance. And then we also have the space for lighter than air airships and blimps, which you see on the buoyant side. And so what we want to do is to go kind of near this buoyant side and start exploring designs and seeing how we can do that. I also introduced a figure on the bottom left that I think was interesting because it's one of the reasons apparently why lighter than air aircraft are interesting is they occupy an interesting space for payload efficiency. So potentially this has interest for an indoor usage for this reason. That is, they can deliver cargo faster than many types of vehicles, and they do so at a relatively good operating cost. So if it comes to things that move faster than land vehicles or sea vehicles, they are great, but they are of course typically much slower than typical aircraft that you would see. So what we hope to get out of this project is we want to design a hybrid aircraft for our Galois needs. And in so doing, to document our designs so that enthusiasts and researchers can recreate them, and then to also create a modeling framework that's broad enough so that we can do some model-based design practices and start simulating or exploring this design space that way. And then we also want to leave our design methods and artifacts accessible so that people can modify their hybrid aircraft and use it for their own needs. So for this project, we came about with a design process in mind. That is, we have key vehicle qualities we want to start off with, and then we want to successively refine it so that we can create a concrete design. And so when it comes to vehicles like this, it's not uncommon to start with payload, range, and maneuverability. And we can start doing very rough cut back of the envelope calculations to understand where we're at in that space. That is, we know roughly how much lift we'll get for a certain hull size using helium, and that could inform us on our shape and our size requirements. We also can start reasoning about how much propulsion we'll want to do to offset the buoyancy of the aircraft, and then that can start feeding our energy calculations. And then after that, you have these more secondary requirements that you'll add on later. These may be more mission specific, but not critical to the flight of the aircraft. Things like communication and some types of sensing. And then the final stage we'll do is we'll start going into refinement, where we create concrete designs. We actually have real subsystems that we can model and build. So this presentation is more of a sketch than anything. So we haven't actually gotten real requirements yet, and we haven't actually turned the crank, so to say, and created a final design. But we know notionally that we want it to fly around the Galois office, and so we can start giving ourselves length requirements. We know that we want to give it a longer mission time than an off-the-shelf quadcopter, that it needs to be affordable because we want it to be accessible to other people, and so forth. And the other one is the customizable payload. That is, how mindful do we have to be for applications? And we're targeting things like AI, ML, and sensing problems. So we have a video on the bottom of somebody taking an off-the-shelf object recognition platform. And the idea is you could put that in a blimp and do something interesting with it. So for the next part of the design process, which is the refinement, we will start having compute requirements and electrical systems that we'll have to be mindful of. And so, of course, there's a feedback here. Your vehicle size and your energy is going to be informed by this potentially. And so this will be the next part of the plan design process. So this is where the electrical subsystems would come in, and we can start creating a loose component diagram illustrating what we'll need. So we'll need some way to store energy, we'll need some way to distribute it to the pieces that require it, and then we'll know we'll need some type of command and control components such as an autopilot, telemetry, etc. And so this also provides loose images of what the parts may look like for that. Next, I'll invite Sam to talk about how we can take this loose diagram and start making it more rigorous and allowing us to look at different properties.
Thanks. Yeah. So as you start going from hand-drawn wireframe diagram to something a little more concrete, we like to use a tool like AADL, which I'm sure many of you are familiar with, but it's a systems description language that offers a pretty rich and relatively well-defined semantics, and also allows authorship of extensions that allow for some verification of static properties within the system. So we can take a hand-drawn wireframe diagram, realize it in AADL, and as we iterate on the design, enrich the diagram in AADL and enrich the properties that we can prove. And you see sort of an example of such a property on the bottom, in that we can assure that a design might float for a particular period of time. That's mostly just algebra across a model of a system. You can use a similar algebra to prove things about maybe power draw or things like that. And as you create a more granular description of your system, you can start reasoning about things like path of encrypted or unencrypted data and control flow from ground station to vehicle, and prove things like this vehicle won't accept unencrypted commands or unauthenticated users. And I think I will pass it off back to Ethan.
Thank you. So the last part of the design process is actually creating the systems themselves, actually synthesizing what these things will look like and be. And so this will start with the CAD model or the geometry of the airship, and then the other supporting systems like energy storage, actuation and sensing. And then if you can extract a model from that, hopefully you'll be able to do a pretty interesting controller design on that, and then you'll have your closed loop control system built and validated. So at Galois, we do have some tools that enable us to design UAVs. And so what I did for this talk was I just simply put together a blimp pretty haphazardly, meaning I didn't choose my parts in any principled way, and certainly not at the level but we mentioned we would at the design process. But this is mostly to kind of show a sketch of what this may look like by showing design artifacts. So what we do, we start off with is a corpus of components that have good properties to them, meaning we know what they are and they're well documented in data sheets. And so that allows us to build models because we have those features to configure it with. So we specify a component graph, and that translates to an assembly, a CAD assembly of a blimp. And in this case, you can see it viewed in the CAD tool Creo. And what it is a blimp. So it has a hull that is non-rigid, and it has some fixed wing components to it. So it has some rear stabilizing fins, and it also has an additional wing on the bottom. And so this blimp is not really made for indoor use, but it's really made to show how you can design a blimp for this objective we created it, which is go over a 3-kilometer racetrack. So we hope to get efficiency both through buoyancy and the fixed wings that we add to it. We also have a few actuators that we chose from our components. So that would be the motors and the propellers. And what we can then do once we have this CAD assembly is we can start doing refined simulations to start extracting things we need to incorporate actuator physics into the dynamic model for the vehicle. So up top in the middle, you see that the airfoil was put through a simulation where we got things like lift and drag coefficients parameterized by angle of attack. And in the middle diagram, you can see that we got the propeller efficiencies. So we know roughly where we want to operate the propellers to be energy efficient. And then there's also the inertial qualities that we want to extract. So that would be the inertial tensor and then the total mass of the system. We can then compile all of these into a vehicle dynamics model, build out a low-level controller for it, build out a high-level controller for it, so it will be a path-following blimp, and then we put it through a racetrack. So you can see here the course that it took, and it seems very well controlled because it's a large racetrack and it has the ability to correct itself very well. It should be also noted that no disturbance modeling was put on this, so it would likely degrade pretty quickly if you had strong wind. We also have mission relevant metrics that come out of this. So we know the total flight distance is length of the racetrack. We know how long it took to travel the racetrack, and that we have the maximum path and hover errors. So the hover time gives you kind of how long the thing can endure its mission, or how long it could, in theory, have its duration. And then the path error tells us how well it performed at its autonomy objective, which is pretty simple for this example.
Ethan, let me give you like a 3 or 4 minute time warning.
Sounds great. Okay, so the next piece that we want to talk about is kind of how would we approach this at Galois given our tooling skills and our lack of airship knowledge, is we can start doing design space exploration. And because we have this pipeline that can take a component graph and translate it into performance metrics that are mission relevant, we can do this manually or in hopefully more of an automated fashion. So for the manual exploration, because this pipeline was originally designed more for propulsion multi-rotor UAVs, I compare a blimp that we created with a quadcopter made with similar parts. And we see that both of them can achieve the course pretty well. The time to traverse is much better for the quadcopter because the trim speed for that is 3 times greater. The path error is also lower for the quadcopter, but we see that its maximum hover time is much less, about 6 times less than what the blimp would be able of performing at. So this was a manual exploration where we just took existing designs and kind of ran them through this process, but we also have the ability to start doing more automated techniques. So the simplest one is component swapping. We can either enumeratively or through some fancier optimization start tweaking parameters of this blimp and getting the performance results. Or we could even start doing novel component compositions where we modify the structure of the UAV for performance reasons. And then the last piece is doing novel component synthesis, so that it is maybe the hull is not great because you have bad interaction effects that occur between the other aerodynamic pieces, and that you would wish to start running an optimization technique towards doing that. And I'll wave my hands here because I don't have a lot of flexibility in what we can talk about here for how we've approached this in the past. So the last point are the next steps. That is, this was more of a sketch than an actual process. And so that we will actually be doing the design process and hopefully beginning results there. And then of course, because we want this to be a real thing, we're going to assemble it and then run it, bring up tests and validation to actually see if our models are any good and have an end-to-end story there. So stay tuned.
Thanks. Niccolo, you have your hands raised.
Yeah. So that was great, Ethan. I have actually a question that actually you touched base a little bit at then. Why did you choose that design? I mean, it seems like you're starting really from the bottom up. So I can see, and probably that's probably what you're planning to do, I guess. But depending on the operation that you want to do, there can be different design you want to use. For example, you can have instead of an under-actuated type of system, you can maybe create a fully actuated, so that it can move in all directions. Or I don't know, the shape of a blimp perhaps instead to be like long can be just like a sphere. So I was just wondering what's your take on that, and what are you thinking about the design principle, because it seems like you're going in that direction.
Yeah, so this definitely shows too much detail, if you will. That is, before you want to make something this refined, you'll want to have high-level justifications why you chose the parts you did. So I mean, I have some very bad high-level justifications. I know that I want to choose a non-symmetric shape so that I don't have too much of a bluff body at the direction of travel. I know that fixed wing will add efficiency for these kind of long duration flights. But you're right. One of the great problems here is that we're not really catering toward blimp needs because the propellers we chose came from a corpus of quadcopter parts. And it's well kind of known in the blimp hobbyist space that you'll often want to gear down your motors and add bigger props because you actually get more efficiency that way. So these results are not very compelling in terms of a good design choice. And that's very much what these first two steps are that we sketched out is for doing, where you'll have the ability to be more selective rather than kind of just enumerative in a very detailed way that is not amenable to creating designs effectively.
Yeah. I just want to add one thing, and perhaps we can talk offline. But several years ago, actually, with my team, we created a tool was called ROSLab, and the idea was to do exactly what they're doing here: try to assemble together different components, and then define a model. But you could start from a specification. That's the idea. I want to have a robot who can go fly fast, carry certain load, do certain operations. So given the specification, we'll create actually the specification for the hardware and the software. So yeah, if you're interested, I can show you the tool and I can send you some reference about that.
That would be fantastic. Yeah, and I would love to hear about sort of design tools that exist in this area, or even just designs, because this is not the first time that someone has approached this topic.
Great, thanks.
Thank you.
Georgios, do you have a quick question?
I guess not so quick, but how much of this can be automated, right? So is it steps? Could you automate the whole process, maybe starting through a template, right? I'm sure you can define many optimization problems here that
so our starting point, and that's a great question, is this component graph that you see here. And potentially parts of this are pretty easy to have maybe AI pieces automate. That is the composition of these components. So this is a very turn the crank sort of pipeline as it currently exists, where we don't even have this CAD model directly. We have a graph that represents a component assembly, and then we can go from that directly to performance results on this particular racetrack. So once you've kind of constructed your mission, you can then start in a more automated fashion, stepping through different designs and evaluating their qualities.
And I will admit that part of my interest in doing this work and looking into some of these early design questions is, in fact, how much of this can we automate? How much of this can we evaluate in an automated way, even if the design still has to be human, right? You may still want human insight in terms of, I want to be, as Ethan said, he came in with some intuitions about, I want it to not be symmetrical in these ways. I'm looking at fixed wings for these reasons, right? But if he can quickly iterate the loop on both refining that to a more concrete thing and or disproving his own assumptions about the problem, maybe in fact he does really want a spherical system, right? And he just doesn't know it yet. If we can provide those tools, that'd be great. But I tend to think that it's really helpful before you build a tool to do something that you should do it by hand once, so that you sort of know where the rough edges are and where things go wrong. So Ethan's going through it once, and we'll see how it comes out. And I'm hoping that some of the modeling work that Sam does helps us build it into the tools a little easier.
Yeah, I'll also bring up one last topic quickly, which is just the idea of symbiotic design. We definitely want to leverage human expertise, and automation typically explores very localized regions or just explores bad designs. So the question is, there's also the human and machine interaction part of how can we have these automated pieces that go out, do things, report their findings back in a meaningful way, or allow a user to direct them in a meaningful way. And so perhaps that could also be a research topic under this umbrella.
So I'm very happy that you guys invited me. I think I've learned a lot through all the talks. One common thing I have seen through most of the talks is these talks have been about reasoning about blimps. And today I'm going to talk about two topics. One has to do a little bit with reasoning about blimps, but the first topic I want to talk about has to do more with reasoning with blimps. So broadly, I'm going to talk about how can we develop ideas of trust using something like a blimp. And then I'm going to talk about some work we have been doing on learning and see if it makes sense to use those ideas in the context of BLIMS. So we have been doing some work recently on trust for multi-agent systems. Multi-agent systems are basically, you have a number of different agents, and here we are interested more in the multi-agent systems where the agents are mobile, so they can move about. They could be cars, they could be UAVs. But the point is that these different agents are trying to coordinate or cooperate in some fashion with either a central or a distributed controller. And typically there's some kind of ground control center or a traffic management authority that is serving as either a central or a distributed controller to make all these different agents behave, right? So the question is, can we put these controllers on blimps? And to set the context for why blimps might be interesting, let me describe some things that we have been doing. So just to set the tone for the problem, we are looking at controlled multi-agent systems. So here we have agents that are supposed to be or assumed to be autonomous. And these agents report their state or the state of other agents to the central or distributed controller. And this controller basically receives observations from agents, gives a sequence of commands to the agents, and can observe some agent actions, for example, within some bounded area. And the assumption made by a lot of these multi-agent coordination systems or algorithms is that agents that are participating in this process are trustworthy. And generally, the assumption is that if everyone is trustworthy, all agents can safely achieve objectives. Okay. So the problem that we are trying to solve is how can agents safely achieve their objectives when some are untrustworthy? And of course, this is also a problem that a lot of people have looked at. But my slightly controversial statement here is that most of the approaches that have looked at this problem have focused on a very pessimistic view of things. So people in security focus primarily on malicious agents who have desire to cause chaos in the system. But people who look at verification focus many times on pessimistic uncertainty of the environment. And people who look at resilience or fault tolerance try to reason about continued operation in the presence of, again, malfunctioning agents. And this kind of pessimistic view may not be suitable for all settings because agents may not be malicious, they could just be faulty. And sensors or actuators could be malfunctioning, and these faults may not be like fixed. They might come and go. They could be transient. Also, the environment in which these agents may be operating may be unreliable because communication may be unreliable or it could be compromised. In all these settings, perhaps using pessimism is not the best model. And I mean, of course, from a formal method safety perspective, we of course like the pessimism that we use to reason about things. But the real problem with pessimism is that it can seriously degrade performance. If we come up with the most stringent safety requirements, our cars will never move, right? So what we are interested in is, can we come up with a notion of trust that allows us to trade off safety versus performance? And of course, to do this, we need yet another definition of trust. There have been lots of different attempts at defining what trustworthiness means. And in the world of trustworthy computing, of course, it means things that are traditionally associated with secure computing or trusted computing. Whereas now there's a huge buzz around the topic of trustworthy AI, where trustworthiness has come to mean various things like accuracy, robustness, fairness, accountability, even ethics or interpretability, right? So what I'm going to propose is a math-free version of a notion of trust, and it's based on some observations on how human beings trust each other. So imagine there's Alice who has hired Bob to complete an app for her company. And Alice asks Bob, would you be able to finish coding this app by the 10th of October? We have a very aggressive deadline. And Bob says, oh, absolutely. And on 8th of October, Bob has already finished the app. It looks amazing. And Alice is very happy. Consider another scenario in which November 1 comes around and the app is still not ready, it still has bugs. And then Bob tells Alice, oh, you know what, I would have totally finished the app, but a dog ate my laptop, right? I mean, such a lame excuse. Consider another scenario. So Alice needs Bob's help to practice this Balloween talk. And Bob says, sorry, I have tons of homework. I can't really help you. Okay, so actually Bob did have homework. And next day what happened is Alice asked Priya, her friend, hey Priya, how was Lion King? You went to see it, right? And Priya says, yeah, it was great. Too bad you and Bob missed it. And Alice says, yeah, Bob had homework and I had this talk to prepare. And then Priya says, yeah, I know. I saw Bob walking home from the lab looking like a zombie at 2 a.m., right? So Priya kind of confirms what Alice thought Bob was doing. Consider another scenario now, okay, where Bob actually did not have homework, but he had tickets to Lion King. And Alice asked Priya, so how was Lion King? And Priya says, it was great, but Bob is such a softie. He cried when that lion died. And then Alice says, wait, what, Bob was with you? And she's like, yes, he didn't tell you, we had such a good time. So in both of these kind of example cases, what's happening is trust is being evaluated based on whether they followed the commands or whether some trusted observer validated them. And in both the first scenario, in both these cases, Alice's trust in Bob kind of increased, whereas in the second scenario, Alice's trust in Bob decreased. Okay. So using these kind of humanistic notions of trust, we try to formalize these notions in an epistemic logic called subjective logic. And again, I promise to be math free, so I'm just trying to give a very high level intuition of what this notion of trust is. It basically has 4 elements. The first element is to gather evidence about what agents in the system are doing. And you can think of the evidence as either a qualitative or quantitative estimate of the agent satisfying some property. And what the trust authority does is it maintains per agent probabilities of belief, disbelief of uncertainty, which is based on the evidence. And then the controller basically uses these trustworthiness values, which are a function of the BDU probabilities, to modulate the control actions. And here the control algorithm that the controller could use could be any of your favorite algorithm. For example, we use reinforcement learning. And there's another element here, which is in the case of the conversation between Alice, Bob, and Priya, we had this other trusted observer, and then Bob was self-reporting his own state, whereas Priya was reporting Bob's state. So you have information coming from different sources. So you kind of need to fuse this information, and you need to define appropriate fusion operators that allow you to update your belief, disbelief, or uncertainty in the system. And roughly, again, what belief means is if the agent satisfies your property, then your belief is going to go up. If the agent does not satisfy the property, your disbelief is going to go up. And if from the evidence you cannot figure out if the property was either satisfied or not satisfied, then your uncertainty is just going to go up. Okay. So we applied this particular notion of trust in the context of autonomous intersection management. So AIM is a protocol that was developed over 10 years ago by people at UT Austin. And the idea there was to get rid of intersections be traffic light free. So basically cars that need to use an intersection send a message to the intersection manager saying, hey, I'm going to be passing through this intersection. This is my current position. This is my current velocity. And here's the lane where I wish to go. And the AIM, the intersection manager, it picks some kind of collision-free schedule using some algorithm, and it basically assigns to each car some kind of a space-time buffer to use. So here in this picture, the green cells represent a space-time buffer for the cars to use. One of the fundamental things about the early versions of the AIM protocol was that it assumed that all cars are trustworthy. That means they're going to strictly follow the commands. They are going to occupy the specified buffers, and they are going to report their locations correctly. The question we asked is, what happens if cars are untrustworthy? What if they are not where they say they are because they're either malicious or faulty or whatever, right? And of course, as you can imagine, chaos can happen, right? Because if a car that's actually to the left of the intersection says I'm to the right of the intersection manager is going to block a period of space-time for that car to pass through, which the car is never going to use. Or cars may actually end up traveling in regions where they might collide with other cars.
Let me give you a 5-minute warning.
Okay, so I'm going to breeze through this. So the idea we had was, let's try to equip agents with a notion of trust. And you can think of it like as a credit score, right? I mean, as we do transactions, our credit ratings go up or down. Similarly, based on cars' behaviors, your car's trustworthiness is going to go up or down. And one could imagine that this trustworthiness could be stored somewhere in the cloud, maybe literally on a balloon that is in a cloud. Sorry for the horrible pun. But basically, whenever new evidence is obtained, you update your value of trust. And the main idea here is decision making could be influenced by trustworthiness, right? So again, just flashing this slide here, what we found in our experiments is that if we use the notion of trust, we get much fewer collisions, but we don't really compromise so much on the performance. So it's not like we make the intersection stop and let only one car pass the intersection. We can allow some amount of concurrency through the intersection, but also use trust to make sure that things remain safe. We've also applied this to a bunch of different scenarios, including cooperative adaptive cruise control, traffic light control, also some recent work that's under submission where we have applied it to the context of perception. But the main ingredients that are required in this approach are we require the ability to watch agents. We kind of swept that under the rug in our initial work. We assume that we can always watch the agents in some bounded area. Well, how could we realize this in the real life? Imagine a blimp that has a camera that is, or several blimps with several cameras watching over the streets of your city. Then you could observe the car's behaviors and based on that, develop a model for trust in individual cars or individual drivers. You also require the ability to do edge computing to gather information from diverse sources and synchronize with some kind of central authority. So you can imagine blimps that are capable of doing edge computing. So I mean, I feel like blimps can become a way of doing some integrated transportation management when you have a hybrid of ground and aerial vehicles, which I have not considered, we have not considered so far. One thing I do want to mention is the idea of a blimp watching me all the time raises the hair on the back of my neck because it seems like a serious privacy violation. We don't want another Facebook in the sky. So trust and privacy have an interesting trade-off. Just to mention it out there, I don't want to go into the details, but that's something we have to be cognizant about. Let me very, very quickly in a minute just breeze through some of the work we have been doing on learning. Deep RL is in the air. Everybody wants to do deep RL, but the problem with deep RL is that unless you design your rewards correctly, you can have unsafe or undesirable policies. And a lot of people try to solve this by doing careful reward shaping. Okay, and there is a lot of very interesting work recently on doing RL from specifications, where the idea is to move away from rewards to specifications and use the specifications to guide what rewards to use for your RL agent. We have been trying to take a slightly different path. In reward shaping from temporal logic specifications, you ideally want all your desirable behaviors to be encoded in the spec, and it's not very easy to incorporate user preferences. So we have been taking a different approach where we are trying to do learning from demonstrations, where demonstrations encode domain knowledge and user preferences. So one way to think about it is specifications tell us what we want to do globally. Demonstrations tell us how we want to do it locally. And the goal is to do what we want to do. We want to figure out how to do what we want to do globally. So we want to learn a policy that works everywhere. So we have a method in which we have combined demonstrations with some high-level temporal logic specifications. And I'll just flash the results here. What we found is in contrast to state-of-the-art learning from demonstrations methods like max causal entropy IRL, which needs 100+ demonstrations in the simple example of going from the top left corner to the top right corner in the presence of some obstacles. We need only 3 demonstrations, and some of those demonstrations could be even wrong or suboptimal. We can allow incomplete or bad demonstrations. We can allow demonstrations which go to multiple goals. We can also have continuous environments or stochastic environments, and we can use ideas like neural networks or Gaussian processes to generalize in these continuous or stochastic spaces. What does this have to do with blimps? So I think you could use this to do things like learning motion planning in presence of winds, etc., from actual pilot maneuvers. Or more generally, take your favorite deep RL research for blimps and just add specifications. It would be interesting to see what we can get out from that. So just to conclude, two main takeaways from this talk. First of all, trust could enable some interesting trade-off between safety and performance, and we could use the notions of trust we could deploy these notions of trust in the real world on a blimp by using a blimp as an observer. And we could also try to do some motion planning for blimps using some formal specifications. All right, so that's all
Great.
I had.
Thank you.
Hey, everybody. My name is Omar Chaudhry. I'm from the University of Iowa. Can you hear me clearly?
We can.
Okay, perfect. So I might be a little loud because giving lectures with masks on, I have this bad habit of like shouting, essentially. So, so today my talk is about taking a principled approach to designing a robust autonomous blimp while embracing pragmatism. I mean, and we're going to talk a little bit about the challenges, potential approaches, and possible path forward. Now, I wanted to give you this disclaimer. My research interest is in security and automated reasoning, intersection of it. So I'm going to be talking about the design of a blimp from that lens. I've done a lot of work on regulatory compliance, authentication, IoT security, privacy, secure communication, like SSL, TLS, cellular network. And recently, I wouldn't say recently, I mean, from 2017, we have been trying to build resilient system by design. Now, and this is the focus of my talk today. And so to do this, let's start with the thought exercise, which that the Balloween workshop is supposed to do, is develop a secure but fully functional system. So the system here is the blimp that we are trying to build. Now, in an ideal world where we did not have any constraints, we would start off with bringing in a lot of experts, which Galois did, and we would try to write a system spec. Different part of it, different expert would write different part of it. Some people would write the control part, some people would write the nonlinear dynamics, and so on and so forth. Now, once this is done, you have a system spec. You then analyze it automatically with some tool. If there are alarms, you fix them with modified system spec, and you keep doing this, iterating this. Once you're happy, you then have a developer who you give the target platform, the system spec, and his job is to write this, like implement this spec for this target system. Now, once this is done, you have the target system, maybe because of abstraction gaps and other things, you would like to test it. So once you test, you can find issues, you fix them, and you keep doing this over and over again. Now, at the final, when we deploy it, attacker comes in, it tries a bunch of attacks, nothing works, right? Now, in this world, people like us do not have a job, right? But we do have a job. So why can't we essentially realize this vision? So this is my opinion of why we can't realize this vision. Now, there are cases when we have weak design, we have weak threat model, because somebody might ask, who did attack a drone or say a blimp on a Galois office? If the blimp was bothering me, I would try to attack it. Like it's flying over outside my office. Or say, in many cases, we are worried about delivering the product, and security is often an afterthought. The other thing is, like, there are these other constraints we have to fulfill, quality of service. Joy was mentioning that if we do not move, I mean, that's kind of takes the productivity away. Then you have domain constraint that it has to be lightweight, because I cannot, it has to be able to fly a lot. Then the other thing is like, it's just lack of incentive in general of why we have to think about security. Now, then there are these other issues like buggy implementation. You have the complexity of the domain, like needing to handle nonlinear like dynamics. And finally, I would say one of the most challenging aspects is large attack surface. It's just attack can come from anywhere. Now, then there are these other things like you're trying to build a secure system. It's going to take you time. It's going to cost you money. And in many cases, you don't have the analysis tools to actually that will enable you to talk about security from the very beginning of the design exercise. And finally, this is often less talked about in a sense that you might have all these fancy tools, but if the people who's using it do not have training or do not know how to interpret some output, it's just a useless exercise, okay? So my talk would focus on the weak design aspect, issue of security as an afterthought, and lack of analysis tools, okay? So cost and other things, unfortunately, is something I'm not credible to talk about. Now, I'll talk a little bit of lack of training too. So one of the things that makes it overall challenging is security is essentially, security or even safety is a trade-off. That is, in many cases, you have, because of security, you have to take away some functional guarantees. Now, where is the line that you say, these are good, these are bad, right? Now, the pragmatic view that we take, at least here at Iowa, is that security and safety issues, you cannot avoid them. So the best you could do is try to hope for some resiliency. That is, it doesn't degrade drastically when it's under attack. Now, so what we are trying to do is develop an automated evaluation tools that allow system architects to actually explore and analyze their system's robustness without needing expert level knowledge in security and safety. Now, so our analysis could be viewed as what if analysis. That is, what if I get this product or this component from some third party, right? And they have a logic bomb inside. Can my system sustain this? Now, to do this kind of analysis, we built this tool called Cyber Resiliency Verifier. And what the Cyber Resiliency Verifier enables is the system designer starts off with a system model. So which would be at some level of abstraction, the architecture or design. So what Ethan showed, and Sam talked a little bit about the AADL. So once you have this, you have to come up with some properties you want to maintain, at least even under attack. Now, these are represented in some logic form. For our case, it's temporal logic. And then what we have is a pre-populated list of threat effect libraries. And then you have a reasoning engine. So to do an analysis, the designer ends up selecting one or more threat effect from the library. And then what it does, it actually gets fusioned into the attacker behavior into the model. So when the designer has to write this, you don't have to worry about how the attacker can manipulate your system design. That's not the job of the designer. Now, what comes out is a fusion model that has the behavior and the attack together. And this is fed into a model checker, infinite state model checker called Kind2. This is developed here at Iowa. And once the model checker will tell you either that, okay, even under this attack, I can ensure that the properties hold. And or in the case it's actually not feasible, you try to see which components misbehavior may have contributed to this bad counterexample, right? So the diagnostic information you get is the violated properties, which properties, because you may try to check multiple properties at the same time, which components and links attack sort of contributed to this, and the actual execution. Now, on top of it, we do provide this thing called merit assignment. So merit assignment could be viewed as identifying critical links whose good behavior contributed to this. Now, this information is very useful when you give it to the developer, you make sure you tell them that these components are very necessary to providing this guarantee, okay? So be very careful when you implement this.
Omar,
Now,
I'm gonna give you a 3 or 4 minute warning.
Okay. So what one question we have is that how do you ensure that like how do we capture these threat models? Because we are at a very high level of abstraction. Now we can start modeling attacks like existing attacks explicitly, but there are too many attacks, right? And in many cases, the applicable attacks are not applicable in the model level, right? So there is no database information, like whether so if you don't have a database, what is there to talk about SQL injection? Then the other thing is you cannot reason about future attacks, right? Attacks that could come in the future. Or whenever there is a new attack, you have to update the model and you're going to be tired. So what we decided is like, let's look at effects of attack, where if you think about attacks, a lot of times the attacker wants to actually run malicious code, bypass the authentication, escalate privilege, or crash the thing, right? Now, the good thing about this, thinking about effects is that rather than trying to explicitly model attack, let's model effects. And there is a small number of them. They do not change often and may allow reasoning about future attacks as long as those attacks have the same effects that you have modeled. And so then what you could do is we have attack effect templates based on these things that you can actually call upon. Now, the next slide, I'm going to skip how we do it. That's not very important. Now, the main challenge is that scalability is an issue because we are using automated reasoning. You have the abstraction gap that for anything usable to be reasoned about, you have to abstract things away. And so the implementation of it might have issues that you couldn't catch in the design level. There are nonlinear dynamics where automated reasoning is very bad at reasoning about them. Then you could have supply chain issues. And the other thing is whenever you have crypto built in, reasoning about all of these together is problematic. Now, what you could do is for scalability, the standard technique is compositional verification. For abstraction gap, you have to make sure you test the implementation. For nonlinear dynamics, you can do lazy combination. I'll talk about it very briefly. And for supply chain issues, that if you were to get it from commercial off the shelf as one component, how do you defend against that? And finally, if you have crypto, you do the same. That is lazy combination of multiple reasoners. So one of the things we did was this tool called LT Inspector that we analyzed the LT model, which essentially follows the same principle that I just showed you, right? And it's fed into a model checker. The thing about this model is that this protocol has crypto, but we abstract the crypto away. And once you do that and feed the desired properties, you fed it into model checker, it's gonna tell you yes and no. Now, when it's no, it could be due to the fact that you abstracted away crypto, okay? And so that we run this by the cryptographic protocol verifier who actually checks whether cryptographically, whether the sequence makes sense, or you could use domain knowledge. And once this is done, you actually run it in the real system and then report attacks. Now, the other thing briefly I'll talk about is defense in depth, this work we did with CMU, where if you have different components coming from different providers, and these things are black boxes, and they have real-time constraints. So one approach you could do is actually start applying runtime monitoring. Now, unlike functional properties, we can check safety rules. Safety rules are, say, if I press the brake, the speed should decrease within the next 5 milliseconds, right? And then you can actually start monitoring it. And whenever there is a violation, you essentially let the command module know, which takes appropriate actions to recover from this. Now, there are a few more slides, but I'll stop here. Thank you for your attention. I have shared these slides with Julie. So if somebody is interested, I think I'll just go to my takeaway message. So my takeaway message is thinking about safety and security from the very beginning. I think it's a good idea, unless there is a reputation. Like, you don't worry about your reputation, because somebody will find an issue and they're going to say, oh, Galois built this thing, doesn't have any security in it, right? And so my overall pitch is that we should try a principled approach while being pragmatic at the same time. I mean, when some things are hard, I mean, we cannot say overnight start reasoning about nonlinear dynamics. I mean, it's not going to happen, right? It's the machinery is just not there. So we could try to use the specialized things that reasons about nonlinear dynamic and just bring in the guarantees and reason about it in the automated reasoning setting. So that's my talk. If you have questions, I'll be more than happy to take them.
So today I'm going to talk about, actually, I'm not going to talk about the work I have already done in the recent years, but I would like to talk something that we are working on. And this is a very, very interesting, this is a framework about investigating the dependency between two parameters or among a group of parameters in a learning-enabled cyber-physical systems. And this is a very, very interesting framework, such that if we study the dependency of those parameters, and the result might help us to answer a lot of interesting safety and security problems on CPS. So here, this is the formal model actually of our learning-enabled CPS. And we can see that clearly this model can be extended a little bit. So we have a plant and we have a controller, and this controller is a neural network, and what I call this decision maker. And we also have a perception component, which helps to estimate the system state. Here we assume that the state perception module is also a neural network. Although I'm using the same figures here, but they can be different. And for the simplest case, this state perception module can be a common filter. So you take the data from the sensors, and then you try to estimate the current state of your plant. And based on the current state and your decision maker, the neural network will compute the control input, which will be sent to the actuators, and the actuators will actually send the actual control inputs to the plant to govern the behavior of this plant. So the interesting thing is that if we represent all of them like a formal model, and we know that both of the neural networks can be represented by formal models because they are just computer programs. And then the plant, we usually use differential equations, which can be nonlinear. So this differential equation may have the state variables, which are denoted by X, and the control inputs, which are denoted by U. So and then we currently assume that the controller takes no time, which means that the control input is computed instantly and then send it back to the system. And in the future, we may extend this model a little bit, but this is a very, very standard formal model we used for learning-enabled CPS. Of course, you may also extend this model a little bit, adding more components there. So let's take a look at the interesting safety and security questions related to this model. And many of these questions actually are from the general cyber-physical systems. For example, the first one could be, is the system safe? Which means that, is it possible for the system execution to reach any unsafe state? The next question is that it's a more general verification. That is, I give a property, and this property might be described by some logic formulas. And then let us see whether this property is satisfied by all of the executions. Or we say whether this property can be violated by some executions. This is more like a falsification. And then the next one will be even more interesting. That is related to security. For example, if our system is under a sensor or actuator disturbance, or maybe an attack, which means that your sensor data is modified, or your actual control inputs, some of the control inputs are actually modified by the attacker. And then the question is that, how can we keep the system safe? Or can we really keep the system safe for a long time period? And finally, both still the similar question, but this question asks us to find the control inputs. So all of these questions are very, very interesting. And actually these questions, of course, there are also more questions related to safety and security. All these questions actually can be studied based on the dependency analysis. Very interesting. Let's take a look at the parameters. What kind of parameters we may consider for this learning-enabled CPS? For example, system state. Definitely system state is a very, very interesting parameter. X, we say X. If the system has multiple
multiple variable state variables, and each state variable can be considered as a parameter. And the sensors, the sensor data. So sensor data, sensor data might not be the actual reflection of the system states because there might be some transformation. If we take every single sensor data as a parameter, and yes, this is also also a variable. And then control input, every control input can be considered as a parameter. If you have multiple control inputs, each of them. And finally, the state estimation. This is the estimation of your current, of an actual system state. This can also be considered as parameters. So all of these parameters actually are time related, which means that they may take different values at different times. For simplicity, I only consider the time at discrete steps, and which means that we define we use a step size delta which is greater than 0. So, and you may change the value of this delta. So if the delta is small, actually you are studying more parameters. If your delta is large, and the values of your parameters will be less if the time is bounded. So this is still discrete. However, your system might not be discrete, which means that your prompt is continuous. But we only check the parameters at discrete time step. So the first dependency problem, the first problem asks this question. So if I have two parameters, doesn't matter this parameter Z1, Z2. This Z1 can be a state variable, and this Z1 can also be a control input. Z2 can be a state estimation, and it can also be a sensor data. So, but they are time related, which means that their value actually we check their values at different time steps, or we are only interested in their values at a particular time step. So they are time related. So assume that Z1 is a parameter, and its initial value is A, is a single value A. And then you can see these blue dots are the reachable values of this Z during the system evolution at these discrete time steps, delta to K delta. And then clearly, because Z1 and Z2 are correlated, Z2 will also have this kind of behavior. So which means that Z2 will start with another value, and then the rest of them are the reachable states. And finally, the Z2 value will be B at K delta. But of course, usually you cannot compute this B, but there will be a value, usually cannot. But the first dependency problem asks this question. If I give a deviation on this A, okay, if I say that I add a deviation, the amount of this deviation is called alpha. Okay, alpha is greater than 0. I added this one. And then what's the maximum deviation we may have on this B? This is the first question. So why we need to study this kind of dependency? Because this deviation might be caused by an attack, or might also be caused by a small disturbance from the environment. Then it helps us to know all possible reachable states of Z2 at the time K delta. If we check the Z2 value at all of these discrete time step, and actually we can compute the reachable states and check all of the possible reachable states according to the safety constraints or properties. Then let's take a look at the interesting questions we may have for this dependency. If both Z1 and Z2 are state variables, actually this is exactly reachability or safety verification problem. And then you may also apply apply the solution to solve more general model checking problems. Why? Because you may consider more Z1, Z2, this kind of dependency of the state variables. And secondly, if Z1 is a state estimation variable, which means this is from the hat X, from your perception neural network, and Z2 is a state variable, then we can see the robustness of the system to the estimation errors. The third one is that Z1, if Z1 is a sensor data and Z2 is a state variable, then the deviation applied to Z1 actually is a disturbance to the sensor. Then we can see what's the robustness of the system with respect to the sensor attack or sensor disturbances. And similarly, we can do very similar analysis for the actuator attacks or actuator disturbances. So we can see all of these 4 questions actually can be studied based on an answer to the first dependency problem. And then the next dependency problem, that is I call this dependency problem 2. That is more challenging. That is we still have a deviation applied to the first parameter Z1 and at a particular time. And then after I apply this deviation, I want to see how long the value of Z2 can stay in the given range. So for example, a very clear application of this problem can be to study the safety of the system under a sensor or actuator attack, right? So for example, if this alpha is applied by a sensor attack at a particular time, then finding the maximum number of steps to keep Z2 in the given range actually can help us to know how long the system can be safe. So answering this kind of question can be very, very important and very interesting. So two applications of this question, that is Z1 is a sensor data and Z2 is a state variable. It is just the case that how long can we keep the system safe during a sensor attack? And similarly, if Z1 is a control input, then this is the answer to how long can we keep the system safe under an actuator attack. So these both of them are very, very important questions we can solve if we can study the dependency. Then the last dependency problem actually is even more challenging than the second one. That is still a deviation applied here, but the question is different. That is, I don't want to see how long I can keep, how long the system can be safe under the original control, under the original neural network controller. But this time I want to see whether or not I can find a sequence of piecewise control input, K-step, a piecewise control sequence to keep Z2 safe. So this is more like a controller synthesis problem. So this question actually, an answer to this question can help us to design a very simple fallback controller. And which means that if there's an attack detector of our system and an attack is detected, then the system can switch to the simple fallback controller. And the fallback controller may apply this piecewise constant control sequence to keep the system safe under an open loop control framework. And when the time is sufficiently long, that is the number of step K is sufficiently long, we can wait for the actuator or the sensor to recover. And then we can give the control back to the original controller. So actually dependency problem 3 actually is the most challenging problem, but actually will be more interesting, So we actually tried this idea, not really on learning enabled CPS. This is our previous work, but on a linear dynamics. We try to design fallback controllers or recovery controllers to keep the system safe under sensor attack. And we have 2 papers published recently at RTSS at EMSoft. And the main idea is like this one. So, but this figure also works for the learning enabled CPS. For example, if an attack,
a 5-minute warning.
Okay, thank you. If an attack is detected at the time T0 plus TA, and we know that the false state, actually the solid execution, this is the view of your controller. Your controller can only see this false state, okay, and the false execution. And then the actual state can be different, which may be closer to the unsafe set. However, under our recovery control, what we can do is that the current controller can still, the fallback controller can still keep the system safe based on the false state, So this is the main idea of the how to against sensor attack. However, the work actually is very challenging. So how to against actuator attacks, this is also a problem. You can see that I raised a lot of problems, very interesting, but at last I'm going to show you some of the results we have. So this is also more interesting problem and very challenging problem. This is actuator attacks. Assume that we have M control inputs, okay? Assume that some of the control inputs are compromised. Then the following 2 questions are like, how long can the current controller keep the system safe? Okay, this is very similar to what we see, but the next one will be more interesting. Is it possible to just use the remaining control inputs and along with a simple fallback controller to keep the system safe before the actuator is recovered? So, which means that if we can know the dependency, or we can find the dependency of the variables, of the parameters, we can we may answer these two questions. So let's take a look at some results we have for to answer the first dependency problem. So we implemented a polynomial arithmetic framework called Polar based on C++. And what we are doing is we only study the first dependency problem, which means that we add the disturbances and try to find the maximum deviations which might be caused in the future states. And we apply this one to study the reachability of neural networks control systems. And this is based on a new version of Flowstar Toolbox. Yes, the Flowstar 2 is greatly improved. Actually, I'm still waiting for some results to put this online. And the current version of Flowstar actually may allow you to do this online verification. So you can see this video. In this video, actually, all of the flow pipes are computed online. The moving vehicle, this racing car, actually is it determines the next step actually based on the prediction, which are the flow pipe over approximations computed online. So we computed like 10 flow pipes every time step, and these 10 flow pipes, the computation time of these 10 flow pipes is around like 5 milliseconds, only 5 milliseconds. So this video is played in the normal speed. It's not accelerated, okay? So then let's see the performance of the first application of the Polar. That is to see the application of the one answer to the simplest version of the dependency problem 1. So this is the result. We evaluate the performance of our method based on this neural network control system. So our dynamics is the plant is defined by a 6-variable nonlinear differential equation, and we have 3 control inputs. And there's no state estimation. We assume that the controller can see all of the system states. And then we can see the flow pipe construction that is based on the dependency analysis. This is not from the basic Flowstar method, but just read dependency analysis method. We studied the data dependencies among the state variables. So the green boxes actually are computed by our dependency analysis result. And those gray boxes, you can see they explode extremely fast. They are actually from VeriSig 2.0, which is published this year at CAF. So you can see our dependency analysis result shows a very, very accurate over approximation set, and it can capture the exact system execution very, very well. Then probably you may ask, in order to achieve this accuracy, how much time you need to spend, right? How much time? Let me tell you, it's very, very less of time. Actually, we spend very less time. These are all of the benchmarks we have. For the previous example, we spent only 3 minutes to perform the computation for 30 time steps. Only 3 minutes. And but this is offline, not online. But for more benchmarks, we make a comparison. We show a comparison to the existing tools. And we compare the Polar techniques implemented in Polar to RichNN, Sherlock, and VeriSig 2.0. And probably you may ask why not the other tools. I'm very sorry. This example, the other tools does not work on this example. We tried more tools, but they don't work. They just don't work. Probably because of the dynamics are nonlinear. So what we can see is that Polar works very, very well here. We spend a very little amount of time. So V, the column V denotes the number of variables of the system. And capital M denotes the number of layers of the neural network controller. And this N, this little case N denotes the number of steps we perform, number of steps. Polar actually only has a low performance at the test number, the second test of number two. That is unknown because no method is perfect. So that's why we actually investigated the reason for this bad performance. This is just because of one of the combination of the polynomial arithmetic. So that polynomial arithmetic result produces a little bit large overestimation. So that's why that is a little bit bad. But for the rest of them, they work very, very fine. So probably you may also ask this question. So how about large scale systems? And how about the case that we try more neurons, we try more layers of neural networks, or we perform more number of steps? So the reason this table does not include them is that the other two does not work. Polar works still very well. The other two does not work. So we actually did not include them. Otherwise, we will see all crosses for other tools. So this is not good. So this table can already show the power of Polar. So, and yes, we are continuing in working on this, working on those questions, and hopefully we will produce more results in the near future. Thank you.
Great. All right. So as
you.
I said, we've been running a little behind, and I think we ate into our some of our Slack, but we do have sort of an open discussion section at the end. If there are some questions that you want to ask any of the speakers from today or yesterday, or just want to broadly talk about safety and security and balloons and so forth, open floor. If there are any questions. I see that there's been some activity in the Google Doc. That's also a great place to capture questions and comments and so forth. So I'll leave the floor open.
I can start with a quick question. Sim, great talk.
Thank you.
Thank you. Going with let's say making interfaces that will be lowering the entry point for using these tools. It would be nice to be able to use these tools in classes and so on, right?
Yeah.
What are your thoughts on that?
Actually no, because what can I say? Because UD, how can I say, our PhD program just started, and also our master program, it's very complicated. I don't want to say some bad things about UD, but UD is a good school, but the average quality of our graduate students are not strong. It's not strong. So that's why in my class, I usually show those very simple, like a control theory, and show them how to build simulators and how to design simple controllers to control those robots implemented by simulators. So that's I can see that is the maximum extent I can do. So if I put any verification techniques there, or they are really, students are really screwed. So that's why.
You know, yeah, sometimes if the tool is there, then at least you can teach on the use of the tool, right? So
yeah,
it would be nice to have this interface.
I'm trying to improve this. I still need to see. Yes, I still need to see. Yes, I know that introducing young students to those verification techniques would be very, very interesting. Yeah.
This is speculative, but I think that would be a nice collaboration opportunity where we can maybe work with Shin and include that in the CSAF tool we have and add a reachability analysis, which is just Shin's flow star and Polar.
Yeah, actually, I tried to release the new version of the toolbox of Flowstar a long time ago, but it's just like disturbed a little bit by my teaching load. So I probably will do something during this winter break. Yeah, thank you.